Hello, my name is Dan Bonet, and I'd like to welcome you to my course on cryptography that I'll be teaching at Stanford University this quarter. This quarter I'm experimenting with recording the lectures and having the students watch the lectures online. In fact, anyone is welcome to watch the lectures and join the course. This is an experiment, so we'll see how it goes. My goals for this course are basically to teach you how cryptographic primitives work. But more importantly, I'd like to teach you how to use cryptographic primitives correctly and reason about the security of your constructions. We will see various abstractions of cryptographic primitives, and we'll do some security proofs. My goal is that by the end of the course, you'll be able to reason about the security of cryptographic constructions and be able to break ones that are not secure. Now, I'd like to say a few words on how I would like you to take the class. First of all, I'm a big believer in taking notes as you listen to the lectures, so I would really encourage you to summarize and take notes in your own words of the material that's being presented. Also, I should mention that on the videos, I'm able to go much faster than I would go in a normal classroom, and so I would encourage you to periodically pause the video and think about the material that's being covered and not move forward until the material is clear in your mind. Also, from time to time, the video will pause and pop-up questions will come up. These are intended to kind of help you along with the material, and I would really encourage you to answer those questions by yourselves rather than skip them. Usually the questions are about the material that has just been covered, and so it shouldn't be too difficult to answer the questions. So I would really encourage you to do them rather than skip them. Now, by now, I'm sure everybody taking the class knows that cryptography is used everywhere computers are. It's a very common tool that's used to protect data. For example, web traffic is protected using a protocol called HTTPS. Wireless traffic, for example, Wi-Fi traffic is protected using the WPA2 protocol that's part of 802.11i. Cell phone traffic is protected using an encryption mechanism in GSM. Bluetooth traffic is protected using cryptography, and so on. We're going to see how these various systems work. In fact, we're going to cover SSL and, in fact, even 802.11i in quite a bit of detail, and you'll see how these systems work in practice. Cryptography is also used for protecting files that are stored on disk by encrypting them, so that if the disk is stolen, the files are not compromised. It's also used for content protection. For example, when you buy DVDs and Blu-ray discs, the movies on these discs are encrypted. In particular, DVD uses a system called CSS, the Content Scrambling System, CSS, and Blu-ray uses a system called AACS. We'll talk about how CSS and AACS work. It turns out that CSS is a fairly easy system to break, and we'll talk about how we'll do some cryptanalysis and actually show how to break encryption that's used in CSS. Cryptography is also used for user authentication and many other applications that we'll talk about in the next segment. Now, I want to go back to secure communication and talk about the case where here we have a laptop trying to communicate with a web server. This is a good time to also introduce our friends Alice and Bob, who are going to be with us throughout the quarter. Essentially, Alice is trying to communicate securely with Bob. Here, Alice is on the laptop and Bob is on the server. The protocol that's used to do that is called HTTPS, but in fact, the actual protocol is called SSL. Sometimes it's called TLS. And the goals of these protocols is basically to make sure that as data travels across the network, an attacker, first of all, can't eavesdrop on this data, and second of all, an attacker can't modify the data while it's in the network. So no eavesdropping and no tampering. Now, as I said, the protocol that's used to secure web traffic, called TLS, actually consists of two parts. The first part is called this handshake protocol, where Alice and Bob talk with one another, and at the end of the handshake, basically a shared secret key appears between the two of them. So both Alice and Bob know this secret key, but an attacker looking at the conversation has no idea what the key K is. Now, the way you establish this secret key, the way you do the handshake, is using public key cryptography techniques, which we're going to talk about in the second part of the course. Now, once Alice and Bob have the shared key, we can use this key to communicate securely by properly encrypting data between them. And in fact, this is going to be the first part of the course, which is essentially once the two sides have a shared secret key, how do they use that secret key to encrypt and protect data that goes back and forth between them. Now, as I said, another application of cryptography is to protect files on disk. So here you have a file that happens to be encrypted, so that even if the disk is stolen, an attacker can't actually read the contents in the file. And if an attacker tries to modify the data on disk, the data in the file while it's on disk, when Alice tries to decrypt this file, that will be detected, and she'll then basically ignore the contents of the file. So we have both confidentiality and integrity for files stored on disk. Now, I want to make a minor philosophical point that in fact storing encrypted files on disk is very much the same as protecting communication between Alice and Bob. In particular, when you store files on disk, it's basically Alice who stores a file today wants to read the file tomorrow. So rather than communicating between two parties, Alice and Bob, in the case of stored disk encryption, it's Alice today who's communicating with Alice tomorrow. But really the two scenarios, secure communications and secure files, are kind of philosophically the same. Now, the building block for securing traffic is what's called symmetric encryption systems. And we're going to talk in the first half of the course extensively about symmetric encryption systems. So in a symmetric encryption system, basically the two parties, Alice and Bob, share a secret key K, which the attacker does not know. Only they know the secret key K. Now they're going to use a cipher which consists of these two algorithms, E and D. E is called an encryption algorithm, and D is called a decryption algorithm. The encryption algorithm takes the message and the key as input and produces a corresponding ciphertext. And the decryption algorithm does the opposite. It takes the ciphertext as input along with the key and produces the corresponding message. Now, a very important point that I'd like to stress, I'm only going to say this once now and never again, but it is an extremely important point, and that is that the algorithms E and D, the actual encryption algorithms, are publicly known. Adversary knows exactly how they work. The only thing that's kept secret is the secret key K. Other than that, everything else is completely public. And it's really important to realize that you should only use algorithms that are public, because those algorithms have been peer-reviewed by a very large community of hundreds of people for many, many, many years. And these algorithms only begin to be used once this community has shown that they cannot be broken, essentially. So in fact, if someone comes to you and says, hey, I have a proprietary cipher that you might want to use, the answer usually should be that you stick to standards, to standard algorithms, and not use a proprietary cipher. In fact, there are many examples of proprietary ciphers that as soon as they were reverse engineered, they were easily broken by simple analysis. Now, even in the simple case of symmetric encryption, which we're going to discuss in the first half of the course, there are actually two cases that we're going to discuss in turn. The first is when every key is only used to encrypt a single message. We call these one-time keys. Okay, so for example, when you encrypt email messages, it's very common that every single email is encrypted using a different symmetric key. Yeah, different symmetric cipher key. Because the key is used to only encrypt one message, there are actually fairly efficient and simple ways of encrypting messages using these one-time keys, and we'll discuss those actually in the next module. Now, there are many cases, in fact, where keys need to be used to encrypt multiple messages. We call these many-time keys. For example, when you encrypt files in a file system, the same key is used to encrypt many, many different files. And it turns out if the key is now going to be used to encrypt multiple messages, we need a little bit of more machinery to make sure that the encryption system is secure. In fact, after we talk about one-time keys, we'll move over and talk about encryption modes that are specifically designed for many-time keys, and we'll see that there are a couple more steps that need to be taken to ensure security in those cases. Okay, the last point I want to make is that there are a couple of important things to remember about cryptography. First of all, cryptography, of course, is a fantastic tool for protecting information in computer systems. However, it's also very important that cryptography has its limitations. First of all, cryptography is really not the solution to all security problems. For example, if you have software bugs, then very often cryptography is not going to be able to help you. Similarly, if you're worried about social engineering attacks, where the attacker tries to fool the user into taking actions that are going to hurt the user, then cryptography is very often actually not going to help you. So it's very important that although it's a fabulous tool, it's not the solution to all security problems. Now, another very important point is that cryptography essentially becomes useless if it's implemented incorrectly. So for example, there are a number of systems that work perfectly fine, and we'll see examples of those systems that in fact allow Alice and Bob to communicate, and in fact messages that Alice sent to Bob, Bob can receive and decrypt. However, because cryptography is implemented incorrectly, the systems are completely insecure. And actually, I should say that I like to mention an old encryption standard called WEP, WEP, that's used for encrypting Wi-Fi traffic. WEP contains many mistakes in it, and often when I want to show you how not to do things in cryptography, I will point to how things were done in WEP as an example. So for me, it's very fortunate to have an example protocol I can point to for how not to do things. And finally, a very important point that I'd like you to remember is that cryptography is not something you should try to invent and design yourself. As I said, there are standards in cryptography, standard cryptographic primitives, which we're going to discuss at length during this course. And primarily, you're supposed to use these standard cryptographic primitives and not invent these primitives yourself. The standards have all gone through many years of review by hundreds of people, and that's not something that's going to happen to an ad hoc design. And as I said, over the years, there are many examples of ad hoc designs that were immediately broken as soon as they were analyzed. Before we start with the technical material, I want to give you a quick overview of what cryptography is about and the different areas of cryptography. So the core of cryptography, of course, is secure communication that essentially consists of two parts. The first is secure key establishment, and then how do we communicate securely once we have a shared key. We already said that secure key establishment essentially amounts to Alice and Bob sending messages to one another, such that at the end of this protocol, there's a shared key that they both agree on, shared key K. And beyond that, beyond just a shared key, in fact, Alice would know that she's talking to Bob, and Bob would know that he's talking to Alice. But a poor attacker who listens in on this conversation has no idea what the shared key is. And we'll see how to do that later on in the course. Now, once they have a shared key, they want to exchange messages securely using this key, and we'll talk about encryption schemes that allow them to do that in such a way that an attacker can't figure out what messages are being sent back and forth, and furthermore, an attacker cannot even tamper with this traffic without being detected. In other words, these encryption schemes provide both confidentiality and integrity. But cryptography does much, much, much more than just these two things, and I want to give you a few examples of that. So the first example I want to give you is what's called a digital signature. So a digital signature basically is the analog of a signature in the physical world. In the physical world, remember, when you sign a document, essentially you write your signature on that document, and your signature is always the same. You always write the same signature on all documents that you want to sign. In the digital world, this can't possibly work, because if the attacker just obtained one signed document for me, he can cut and paste my signature onto some other document that I might not have wanted to sign. And so it's simply not possible in the digital world that my signature is the same for all documents that I want to sign. So we're going to talk about how to construct digital signatures in the second half of the course. It's really quite an interesting primitive, and we'll see exactly how to do it. Just to give you a hint, the way digital signatures work is basically by making the digital signature be a function of the content being signed. So an attacker who tries to copy my signature from one document to another is not going to succeed, because the signature on the new document is not going to be the proper function of the data in the new document. And as a result, the signature won't verify. And as I said, we're going to see exactly how to construct digital signatures later on, and then we'll prove that those constructions are secure. Another application of cryptography that I wanted to mention is anonymous communication. So here, imagine user Alice wants to talk to some chat server Bob. And perhaps she wants to talk about a medical condition, and so she wants to do that anonymously so that the chat server doesn't actually know who she is. Well, there's a standard method called a mixnet that allows Alice to communicate over the public internet with Bob through a sequence of proxies, such that at the end of the communication, Bob has no idea who it just talked to. The way mixnets work is basically as Alice sends her messages to Bob through a sequence of proxies, these messages get encrypted and decrypted appropriately so that Bob has no idea who it talked to, and the proxies themselves don't even know that Alice is talking to Bob, or that actually who's talking to who more generally. One interesting thing about this anonymous communication channel is it's bidirectional. In other words, even though Bob has no idea who it's talking to, he can still respond to Alice, and Alice will get those messages. Once we have anonymous communication, we can build other privacy mechanisms. And I want to give you one example, which is called anonymous digital cash. Remember that in the physical world, if I have a physical dollar, I can walk into a bookstore and buy a book, and the merchant would have no idea who I am. The question is whether we can do the exact same thing in the digital world. In the digital world, basically, Alice might have a digital dollar coin, and she might want to spend that digital dollar at some online merchant, perhaps some online bookstore. Now, what we'd like to do is make it so that when Alice spends her coin at the bookstore would have no idea who Alice is. So we provide the same anonymity that we get from physical cash. Now, the problem is that in the digital world, Alice can take the coin that she had, this $1 coin, and before she spent it, she can actually make copies of it. And then all of a sudden, instead of having just $1 coin, now all of a sudden she has $3 coins, and they're all the same, of course. And there's nothing preventing her from taking those replicas of the dollar coin and spending it at other merchants. And so the question is, how do we provide anonymous digital cash, but at the same time also prevent Alice from double spending the dollar coin at different merchants? In some sense, there's a paradox here where anonymity is in conflict with security, because if we have anonymous cash, there's nothing to prevent Alice from double spending the coin, and because the coin is anonymous, we have no way of telling who committed this fraud. And so the question is, how do we resolve this tension? And it turns out it's completely doable, and we'll talk about anonymous digital cash later on. Just to give you a hint, I'll say that the way we do it is basically by making sure that if Alice spends the coin once, then no one knows who she is. But if she spends the coin more than once, all of a sudden her identity is completely exposed, and then she could be subject to all sorts of legal problems. And so that's how anonymous digital cash would work at a high level, and we'll see how to implement it later on in the course. Another application of cryptography has to do with more abstract protocols. But before I state the general results, I want to give you two examples. So the first example has to do with election systems. So here's the election problem. Suppose we have two parties, Party 0 and Party 1, and voters vote for these parties. So for example, this voter could have voted for Party 0, this voter voted for Party 1, and so on. So in this election, Party 0 got 3 votes, and Party 2 got 2 votes. So the winner of the election, of course, is Party 0, but more generally, the winner of the election is the party who receives the majority of the votes. Now, the voting problem is the following. The voters would somehow like to compute the majority of the votes, but do it in such a way such that nothing else is revealed about their individual votes. Okay, so the question is how to do that. And to do so, we're going to introduce an election center who's going to help us compute the majority, but keep the votes otherwise secret. And what the parties will do is they will each send a funny encryption of their votes to the election center in such a way that at the end of the election center is able to compute and output the winner of the election. However, other than the winner of the election, nothing else is revealed about the individual votes. The individual votes otherwise remain completely private. Of course, the election center is also going to verify that this voter, for example, is allowed to vote and that the voter has only voted once. But other than that information, the election center and the rest of the world learn nothing else about that voter's vote other than the result of the election. So this is an example of a protocol that involves 6 parties. In this case, there are 5 voters and 1 election center. These parties compute amongst themselves, and at the end of the computation, the result of the election is known, but nothing else is revealed about the individual inputs. Now, a similar problem comes up in the context of private auctions. So in a private auction, every bidder has his own bid that he wants to bid. And now suppose the auction mechanism that's being used is what's called a victory auction, where the definition of a victory auction is that the winner is the highest bidder, but the amount that the winner pays is actually the second highest bid. So he pays the second highest bid. Okay, so this is a standard auction mechanism called the victory auction. And now what we'd like to do is basically enable the participants to compute, to figure out who the highest bidder is and how much he's supposed to pay. But other than that, all other information about the individual bids should remain secret. So for example, the actual amount that the highest bidder bid should remain secret. The only thing that should become public is the second highest bid and the identity of the highest bidder. So again, now the way we will do that is we'll introduce an auction center, and in a similar way, essentially everybody will send their encrypted bids to the auction center. The auction center will compute the identity of the winner, and in fact, he will also compute the second highest bid. But other than these 2 values, nothing else is revealed about the individual bids. Now, this is actually an example of a much more general problem called secure multi-party computation, and let me explain what secure multi-party computation is about. So here, basically, abstractly, the participants have a secret input to themselves. So in the case of an election, the inputs would be the votes. In the case of an auction, the inputs would be the secret bids. And then what they'd like to do is compute some sort of a function of their inputs. Again, in the case of an election, the function is the majority. In the case of auction, the function happens to be the second highest largest number among x1 to x4. And the question is, how can they do that such that the value of the function is revealed, but nothing else is revealed about the individual votes? So let me show you kind of a dumb, insecure way of doing it. What we do is we introduce a trusted party. And then this trusted authority basically collects individual inputs, and it kind of promises to keep the individual inputs secret so that only it would know what they are, and then it publishes the value of the function to the world. So the idea is now that the value of the function became public, but nothing else is revealed about the individual inputs. But of course, you got this trusted authority that you got to trust, and if for some reason it's not trustworthy, then you have a problem. And so there's a very central theorem in crypto. It really is quite a surprising fact that says that any computation you'd like to do, any function f you'd like to compute, that you can compute with a trusted authority, you can also do without a trusted authority. Let me at a high level explain what this means. Basically what we're going to do is we're going to get rid of the authority, so the parties are actually not going to send their inputs to the authority, and in fact there's no longer going to be an authority in the system. Instead, what the parties are going to do is they're going to talk to one another using some protocol, such that at the end of the protocol, all of a sudden the value of the function becomes known to everybody, and yet nothing other than the value of the function is revealed. In other words, the individual inputs is still kept secret. But again, there is no authority. There's just a way for them to talk to one another such that the final output is revealed. So this is a fairly general result. It's kind of a surprising fact that this is at all doable, and in fact it is, and towards the end of the class we'll actually see how to make this happen. Now, there are some applications of cryptography that I can't classify in any other way other than to say that they're purely magical. Now, let me give you two examples of that. So the first is what's called privately outsourcing computation. So I'll give you an example of a Google search just to illustrate the point. So imagine Alice has a search query that she wants to issue. It turns out that there are very special encryption schemes such that Alice can send an encryption of her query to Google, and then because of the property of the encryption scheme, Google can actually compute on the encrypted values without knowing what the plaintext are. So Google can actually run its massive search algorithm on the encrypted query and recover an encrypted results. Okay? Google would send the encrypted results back to Alice, Alice would decrypt, and then she would receive the results. But the magic here is all Google saw was just encryptions of her queries and nothing else. And so Google, as a result, has no idea what Alice just searched for, and nevertheless, Alice actually learned exactly what she wanted to learn. Okay, so these are magical kind of encryption schemes. They're fairly recent. This is only a new development from about 2 or 3 years ago that allows us to compute on encrypted data, even though we don't really know what's inside the encryption. Now, before you rush off and think about implementing this, I should warn you that this is really, at this point, just theoretical in the sense that running a Google search on encrypted data probably would take 1 billion years. But nevertheless, just the fact that this is doable is already really surprising and is already quite useful for relatively simple computations. So in fact, we'll see some applications of this out later on. The other magical application I want to show you is what's called zero knowledge. And in particular, I'll tell you about something called the zero knowledge proof of knowledge. So here, what happens is there's a certain number n which Alice knows, and the way the number n was constructed is as a product of two large primes. So imagine here we have two primes, p and q. Each one you can think of it as like 1,000 digits. And you probably know that multiplying 2,000 digit numbers is fairly easy. But if I just give you their product, figuring out their factorization into primes is actually quite difficult. And in fact, we're going to use the fact that factoring is difficult to build public key crypto systems in the second half of the course. Okay, so Alice happens to have this number n, and she also knows the factorization of n. Now Bob just has the number n. He doesn't actually know the factorization. Now the magical fact about the zero knowledge proof of knowledge is that Alice can prove to Bob that she knows the factorization of n. Yeah, she can actually give this proof to Bob that Bob can check and become convinced that Alice knows the factorization of n. However, Bob learns nothing at all about the factors p and q. And this is provable. Bob absolutely learns nothing at all about the factors p and q. And this statement actually is very, very general. This is not just about proving the factorization of n. In fact, almost any puzzle that you want to prove that you know an answer to, you can prove it in zero knowledge. So if you have a crossword puzzle that you've solved, well, maybe crosswords is not the best example, but if you have like a Sudoku puzzle, for example, that you want to prove that you've solved, you can prove it to Bob in a way that Bob would learn nothing at all about the solution, and yet Bob would be convinced that you really do have a solution to this puzzle. Okay, so those are kind of magical applications. And so the last thing I want to say is that modern cryptography is a very rigorous science, and in fact, every concept we're going to describe is going to follow 3 very rigorous steps. Okay, and we're going to see these 3 steps again and again and again, so I want to explain what they are. So the first thing we're going to do when we introduce a new primitive, like a digital signature, is we're going to specify precisely what the threat model is. That is, what can an attacker do to attack a digital signature, and what is his goal in forging signatures. Okay, so we're going to define exactly what does it mean for a signature, for example, to be unforgeable. Unforgeable. Okay, and I'm giving digital signatures just as an example. For every primitive we describe, we're going to precisely define what the threat model is. Then we're going to propose a construction, and then we're going to give a proof that any attacker that's able to attack the construction under this threat model, that attacker can also be used to solve some underlying hard problem. And as a result, if the problem really is hard, that actually proves that no attacker can break the construction under the threat model. Okay, but these 3 steps are actually quite important. In the case of signatures, we'll define what it means for a signature to be unforgeable, then we'll give a construction, and then, for example, we'll say that anyone who can break our construction can then be used to, say, factor integers, which is believed to be a hard problem. Okay, so we're going to follow these 3 steps throughout, and you'll see how this actually comes about. Okay, so this is the end of the segment, and then in the next segment we'll talk a little bit about the history of cryptography. Before we start with the technical material, I want to tell you a little bit about the history of cryptography. There's a beautiful book on this topic by David Kahn called The Codebreakers that covers the history of cryptography all the way from the Babylonian era to the present. Here I'm just going to give you a few examples of historical ciphers, all of which are badly broken. So to talk about ciphers, the first thing I'm going to do is introduce our friends Alice and Bob, who are going to be with us for the rest of the quarter. So Alice and Bob are trying to communicate securely, and there is an attacker who's trying to eavesdrop on their conversation. So to communicate securely, they're going to share a secret key, which I'll denote by K. They both know this secret key, but the attacker does not know anything about this key K. So now they're going to use a cipher, which is a pair of algorithms, an encryption algorithm denoted by E and a decryption algorithm D. These algorithms work as follows. The encryption algorithm E takes the message M as inputs, and it takes as inputs the key K. I'm going to put a wedge above the key input just to denote the fact that this input is really the key input. And then it outputs a ciphertext, which is the encryption of the message M using the key K. I'm always going to write the key first, and when I write colon equals, what I mean is that the expression defines what the variable C stands for. Now the ciphertext is transmitted over the internet to Bob somehow. Actually, it could be transmitted over the internet, could be transmitted using an encrypted file system. It doesn't really matter. But when the ciphertext reaches Bob, he can plug it into the decryption algorithm and give the decryption algorithm the same key K. Again, I'm going to put a wedge here as well to denote the key input. And the decryption algorithm outputs the original plaintext message. Now, the reason we say that these are symmetric ciphers is that both the encryptor and decryptor actually use the same key K. As we'll see later in the course, there are ciphers where the encryptor uses one key and the decryptor uses a different key. But here we're just going to focus on symmetric ciphers where both sides use the same key. Okay, so let me give you a few historic examples of ciphers. The first example, the simplest one, is called a substitution cipher. I'm sure all of you played with substitution ciphers when you were in kindergarten. Basically, a key for a substitution cipher is a substitution table that basically says how to map letters. So here, for example, the letter A would be mapped to C, the letter B would be mapped to W, the letter C would be mapped to N, so on and so forth, and then the letter Z would be mapped, say, to A. So this is one example of a key for a substitution cipher. So just to practice the notation we introduced before, the encryption of a certain message using this key, let's say the message is B, C, Z, A, the encryption of this message using this key here would be, is done by substituting one letter at a time. So B becomes W, C becomes N, Z becomes A, and A becomes C. So the encryption of BCZA is WNAC, and this defines the ciphertext. Similarly, we can decrypt the ciphertext using the same key, and of course we'll get back the original message. Okay, so just for historical reasons, there's one example of something that's related to the substitution cipher called the Caesar cipher. The Caesar cipher actually is not really a cipher at all, and the reason is that it doesn't have a key. What a Caesar cipher is basically a substitution cipher where the substitution is fixed, namely it's a shift by 3. So A becomes D, B becomes E, C becomes F, and so on and so forth. What is it? Y becomes B, and Z becomes C. It's a fixed substitution that's applied to all plaintext messages. So again, this is not a cipher because there is no key. The key is fixed. So if an attacker knows how our encryption scheme works, he can easily decrypt the message. The key is not random, and therefore decryption is very easy once you understand how the scheme actually works. Okay, so now let's go back to the substitution cipher where the keys really are chosen at random. These substitution tables are chosen at random. And let's see how we break this substitution cipher. Turns out to be very easy to break. The first question is, how big is the key space? How many different keys are there, assuming we have 26 letters? So I hope all of you said that the number of keys is 26 factorial because a substitution key is simply a table, a permutation of all 26 letters. The number of permutations of 26 letters is 26 factorial. If you calculate this out, 26 factorial is about 2 to the 88, which means that describing a key in a substitution cipher takes about 88 bits. So each key is represented by about 88 bits. Now, this is a perfectly fine size for a key space. In fact, we're going to be seeing ciphers that are perfectly secure that are adequately secure with key spaces that are roughly of this size. However, even though the substitution cipher has a large key space of size 2 to the 88, it's still terribly insecure. So let's see how to break it. And to break it, we're going to be using letter frequencies. So the first question is, what is the most frequent letter in English text? So I imagine all of you know that, in fact, E is the most common letter. And that is going to, if we make that quantitative, that's going to help us break a substitution cipher. So just given the ciphertext, we can already recover the plaintext. So the way we do that is, first of all, using frequencies of English letters. So here's how this works. So you give me an encrypted message using a substitution cipher. All I know is that the message is in English, the plaintext is in English. And I know that the letter E is the most frequent letter in English, and in fact it appears 12.7% of the time in standard English text. So what I'll do is I'll look at the ciphertext you gave me, and I'm going to count how many times every letter appears. Now, the most common letter in the ciphertext is going to be the encryption of the letter E with very high probability. So now I'm able to recover one entry in the key table, namely now I know what the letter E maps to. The next most common letter in English is the letter T, that appears about 9.1% of the time. So now again, I count how many times each letter appears in the ciphertext, and the second most frequent letter is very likely to be the encryption of the letter T. So now I've recovered the second entry in the key table. And I can continue this way. In fact, the letter A is the next most common letter. It appears 8.1% of the time. So now I can guess that the third most common letter in the ciphertext is the encryption of the letter A, and now I've recovered 3 entries in the key table. Well, so now what do? The remaining letters in English appear roughly the same amount of time, other than some rare letters like Q and X. But we're kind of stuck at this point. We figured out 3 entries in the key table, but what do we do next? So the next idea is to use frequencies of pairs of letters. Sometimes these are called digrams. So what I'll do is I'll count how many times each pair of letters appears in the ciphertext. And I know that in English, the most common pairs of letters are things like HE, AN, IN, I guess TH is another common pair of letters. And so I know that the most common pair of letters in the ciphertext is likely to be the encryption of one of these 4 pairs. And so by trial and error, I can sort of figure out more elements in the key table. And again, by more trial and error, this way, by looking at trigrams, I can actually figure out the entire key table. So the bottom line here is that in fact this substitution cipher is vulnerable to the worst possible type of attack, namely a ciphertext only attack. Just given the ciphertext, the attacker can recover the decryption key and therefore recover the original plaintext. So there's really no point in encrypting anything using a substitution cipher because the attacker can easily decrypt it all. You might as well send your plaintext completely in the clear. So now we're going to fast forward to the Renaissance, and I guess we're moving from the Roman era to the Renaissance, and look at a cipher designed by a fellow named Vigenère who lived in the 16th century. He designed a couple of ciphers. Here I'm going to show you a variant of one of his ciphers. This is called a Vigenère cipher. So in a Vigenère cipher, the key is a word. In this case, the word is crypto. It's got 6 letters in it. And then to encrypt the message, what you do is you write the message under the key. So in this case, the message is, "What a nice day today." And then you replicate the key as many times as needed to cover the message. And then the way you encrypt is basically you add the key letters to the message letters modulo 26. So just to give you an example here, for example, if you add Y and A, you get Z. If you add T and A, you get U. And you do this for all the letters. And remember, whenever you add modulo 26. So if you go past Z, you go back to A. So that's the Vigenère cipher. And in fact, decryption is just as easy as encryption. Basically, the way you would decrypt is, again, you would write the ciphertext under the key, you would replicate the key, and then you would subtract the key from the ciphertext to get the original plaintext message. So breaking a Vigenère cipher is actually quite easy. Let me show you how you do it. The first thing we need to do is we need to assume that we know the length of the key. So let's just assume we know that. In this case, the length of the key is 6. And then what we do is we break the ciphertext into groups of 6 letters each. Okay, so we're going to get a bunch of groups like this. Each one contains 6 letters. And then we're going to look at the first letter in each group. Okay, so in this case, yes, we're looking at the first letter every 6 characters. Now, what do we know about these 6 letters? We know that, in fact, they're all encrypted using the same letter in the ciphertext. All of these are encrypted using the letter C. In other words, ZLW is a shift by 3 of the plaintext letters. So if we collect all these letters, then the most common letter among the set is likely to be the encryption of E. Right? E is the most common letter in English. Therefore, if I look at every 6th letter, the most common letter in that set is likely to be the encryption of the letter E. Aha! So let's just suppose that, in fact, the most common letter every 6th letter happens to be the letter H. Then we know that E plus the first letter of the key is equal to H. That says that the first letter of the key is equal to H minus E. And in fact, that is the letter C. So now we've recovered the first letter of the key. And now we can continue doing this with the second letter. So we look at the second letter in every group of 6 characters. And again, we repeat the same exercise. We find the most common letter among this set. And we know that this most common letter is likely the encryption of E. And therefore, whatever this most common letter is, if we subtract E from it, we're going to get the second letter of the key. And so on and so forth with the third letter every 6 characters. And this way we recover the entire key, and that allows us to decrypt the message. Now, the only caveat is that I had to assume ahead of time that I know the length of the key, which in this case is 6. But if I don't know the length of the key ahead of time, that's not a problem either. What I would do is I would run this decryption procedure assuming the key length is 1. Then I'd run it assuming the key length is 2. Then I would run it assuming the key length is 3. And so on and so on and so on until finally I get a message, I get a decryption that makes sense, that's sensical. And once I do that, I know that I've kind of recovered the right length of the key. And I know that I've also recovered the right key and therefore the right message. Okay, so very, very quickly you can recover, you can decrypt Vigenère ciphers. Again, this is a ciphertext only attack. The interesting thing is that Vigenère had a good idea here. This addition mod 26
is actually a good idea, and we'll see that later, except it's executed very poorly here. And so we'll correct that a little bit later. Okay, we're going to fast forward now from the Renaissance to the 19th century, where everything became electric. And so people wanted to design ciphers that use electric motors. In particular, these ciphers are called rotor machines because they use rotors. So an early example is called a Hebron machine, which uses a single rotor. Here you have a picture of this machine. The motor, I guess the rotor is over here, and the secret key is captured by this disk here. It's embedded inside of this disk, which rotate by 1 notch every time you press a key on the typewriter. Okay, so every time you hit a key, the disk rotates by 1 notch. Now, what does this key do? Well, the key actually encodes a substitution table. So, and therefore the disk actually is the secret key. And as I said, this disk encodes a substitution table. In this case, if you happen to press C as the first letter, output would be the letter T. And then the disk would rotate by 1 notch. After rotating by 1 notch, the new substitution table becomes the one shown here. You see that E basically moves up, and then the remaining letters moves down. So imagine this is basically a 2-dimensional rendering of the disk rotating by 1 notch. Then you press the next letter, and the disk rotates again. You notice again N moved up, and the remaining letters moved down. So in particular, if we hit the letter C 3 times, the first time the output would be T. The second time the output would be S, and the third time the output would be K. So this is how this single rotor machine works. And as it turned out, very quickly after it was advertised, it was again broken basically using letter frequencies, digram frequencies, and trigram frequencies. It's not that hard, given enough ciphertext, to directly recover the secret key and then the message. Again, a ciphertext only attack. So to kind of work against these frequency attacks, these statistical attacks, these rotor machines became more and more complicated over time, until finally, I'm sure you've all heard of the Enigma. The Enigma is kind of a complicated rotor machine. It uses 3, 4, or 5 rotors. There are different versions of the Enigma machine. Here you see an example of the Enigma machine with 3 rotors. The secret key in the Enigma machine is the initial setting of the rotors. Okay, so in the case of 3 rotors, there would be 26 cube possible different keys. When you type on the typewriter, basically these rotors here rotate at different rates. Oh, I forgot to say, this is a diagram of an Enigma machine using 4 rotors. As you type on the typewriter, the rotors rotate and output the appropriate letters of the ciphertext. So in this case, the number of keys is 26 to the 4th, which is 2 to the 18, which is actually relatively a small key space. Today, you can kind of brute force search using a computer through 2 to the 18 different keys very, very quickly. You know, my wristwatch can do it in just a few seconds, I guess. And so this Enigma machine was using relatively small key spaces, but I'm sure you've all heard that the British cryptographers at Bletchley Park were able to mount ciphertext-only attacks on the Enigma machine. They were able to decrypt German ciphers back in World War II, and that played an important role in many different battles during the war. After the war, I guess that was the end kind of the mechanical age, and started the digital age, where folks were using computers. And as the world kind of migrated to using computers, the government realized that it's buying a lot of digital equipment from industry. And so it wanted industry to use a good cipher, so that when it buys equipment from industry, it would be getting equipment with a decent cipher. And so the government put out this request for proposal for a data encryption standard, a federal data encryption standard. And we're going to talk about this effort in more detail later on in the course. But in 1974, a group at IBM put together a cipher that became known as DES, the Data Encryption Standard, which became a federal standard for encrypting data. The key space for DES is 2 to the 56, which is relatively small these days, but was large enough back in 1974. And another interesting thing about DES is, rather than, unlike rotor machines, which encrypt 1 character at a time, the data encryption standard encrypts 64 bits at a time, namely 8 characters at a time. And we'll see the significance of this later on in the course. Because DES uses such a small key space, these days it can be broken by a brute force search. And so these days, DES is considered insecure and should not be used in projects. Unfortunately, it is used in some legacy systems, but it definitely is on its way out and definitely should not be used in new projects. Today, there are new ciphers, things like the Advanced Encryption Standard, which uses 128-bit keys. Again, we'll talk about the Advanced Encryption Standard in much more detail later on in the course. There are many, many other types of ciphers. I mentioned Salsa 20 here. We'll see why in just a minute. But this is all for the quick historical survey, and now we can get into the more technical material.
Over the years, many natural cryptographic constructions were found to be insecure. In response, modern cryptography was developed as a rigorous science where constructions are always accompanied by a proof of security. The language used to describe security relies on discrete probability. In this segment and the next, I'll give a quick overview of discrete probability, and I point to this Wikibooks article over here for a longer introduction. Discrete probability is always defined over a universe, which I'll denote by U, and this universe in our case is always going to be a finite set. In fact, very commonly, our universe is going to be simply the set of all n-bit strings, which here is denoted by 0, 1 to the n. So for example, the set 0, 1 squared is the set of all 2-bit strings, which happens to be the string 0, 0, 0, 1, 1, 0, and 1, 1. So there are 4 elements in this set, and more generally, in the set 0, 1 to the n, there are 2 to the n elements. Now, a probability distribution over this universe U is simply a function which I'll denote by P, and this function, what it does is it assigns to every element in the universe a number between 0 and 1. And this number is what I'll call the weight or the probability of that particular element in the universe. Now there's only one requirement on this function P, and that is that the sum of all the weights sum up to 1. That is, if I sum the probability of all elements x in the universe, what I end up with is the number 1. So let's look at a very simple example, looking back to our 2-bit universe, so 0, 0, 0, 1, 1, 0, and 1, 1, and you can consider the following probability distribution, which, for example, assigns to the element 0, 0 the probability 1/2, the element 0, 1, we assign the probability 1/8, to 1, 0, we assign the probability 1/4, and to 1, 1, we assign the probability 1/8. Okay, and you can see that if we sum up these numbers, in fact, we get 1, which means that this probability P is, in fact, the probability distribution. Now, what these numbers mean is if I sample from this probability distribution, I'll get the string 0, 0 with probability 1/2, I'll get the string 0, 1 with probability 1/8, and so on and so forth. So now that we understand what a probability distribution is, let's look at 2 classic examples of probability distributions. The first one is what's called the uniform distribution. The uniform distribution assigns to every element in the universe exactly the same weight. I'm going to use U between 2 bars to denote the size of the universe U, that is the number of elements in the universe. And since we want the sum of all the weights to sum up to 1, and we want all these weights to be equal, what this means is that for every element x in the universe, we assign a probability of 1 over U. So in particular, if we look at our example, the uniform distribution on the set of 2-bit strings would simply assign 1/4, the weight 1/4 to each one of these strings. And clearly, the sum of all the weights sums up to 1. What this means is that if I sample at random from this distribution, I'll get a uniform sample across all 2-bit strings. So all of these 4-bit strings are equally likely to be sampled by this distribution. Another distribution that's very common is what's called the point distribution at the point x0. And what this point distribution does is basically it puts all the weights on a single point, namely x0. So here we assign to the point x0 all the weight, 1, and then to all other points in the universe, we assign the weight 0. And by the way, I want to point out that this inverted A here should be read as for all. So all this says is that for all x that are not equal to x0, the probability of that x is equal to 0. So again, going back to our example, a point distribution, for example, that would put all its mass on the string 1, 0 would assign the probability 1 to the string 1, 0 and 0 to all other strings. So now if I sample from this distribution, pretty much I'm always guaranteed to always sample the string 1, 0 and never sample any of the other strings. So now we know what a distribution is, and I just want to make one last point, and that is that because this universe U is always going to be a finite set for us, we can actually write down the weights that the distribution assigns to every element in U and represent the entire distribution as a vector. So here, for example, if we look at the universe of all 3-bit strings, we can literally write down the weight that the distribution assigns to the string 0, 0, 0, then the weight that the distribution assigns to the string 0, 0, 1, and so on and so forth. And you can see that we can write this as a vector. In this case, it'll be a vector of dimension 8. There are 8 strings of 3 bits. And as a result, basically, the entire distribution is captured by this vector of 8 real numbers in the interval 0 to 1. The next thing I want to do is define the concept of an event. So consider a subset A of our universe, and I'll define the probability of this subset to be simply the sum of the weights of all the elements in the set A. In other words, I'm summing over all x in A the weight of these elements x in the set A. Now, because the sum over the entire universe of all weights needs to be 1, this means that if we look at the probability of the entire universe, basically we get 1. And if we look at the probability of a subset of the universe, we're going to get some number in the interval 0 to 1. And we say that the probability of this set A is the sum, which is a number between 0 and 1. And I'll tell you that a subset A of the universe is called an event, and the probability of the set A is called the probability of that event. So let's look at a simple example. So suppose we look at the universe U, which consists of all 8-bit strings, right? So the size of this universe U is 256 because there are 256 8-bit strings. Essentially, we're looking at all byte values, all 256 possible byte values. Now, let's define the following event. Basically, the event is going to contain all bytes, so all 8-bit strings in our universe, such that the 2 least significant bits of the byte happens to be 1, 1. So for example, if we look at 0, 1, 0, 1, 1, 0, 1, 0, that's an element in the universe that's not in the set A. But if we change this 0 to a 1, then that's an element in the universe which is in our set A. And now let's look at the uniform distribution over the universe U. And let me ask you, what is the probability of the event A? So what is the probability that when we choose a random byte, the 2 least significant bits of that byte happens to be 1, 1? Well, the answer is 1/4. And the reason that's true is because it's not too difficult to convince yourself that of the 256 8-bit strings, exactly 64 of them, 1/4 of them, end in 1, 1. And the probability of each string, since we're looking at the uniform distribution, the probability of each string is exactly 1 over the size of the universe, namely 1 over 256. And the product of these 64 elements, each one has weight 1 over 256, is exactly 1/4, which is the probability of the event A that we were looking at. So a very simple bound on the probability of events is called the union bound. So imagine we have 2 events, A1 and A2. So these are both subsets of some universe U. And we want to know what is the probability that either A1 occurs or A2 occurs. In other words, what is the probability of the union of these 2 events? This little U here denotes the union of the 2 sets. So the union bound tells us that the probability that either A1 occurs or A2 occurs is basically less than the sum of the 2 probabilities. And that's actually quite easy to see. So simply look at this picture here. You can see that when we look at the sum of the 2 probabilities, we're basically summing the probability of all the elements in A1, all the elements in A2, and you realized we kind of double summed these elements in the intersection. They get summed twice here on the right-hand side. And as a result, the sum of the 2 probabilities is actually going to be larger than or equal to the actual probability of the union of A1 and A2. So that's the classic union bound. And in fact, I'll tell you that if the 2 events are disjoint, in other words, their intersection is empty, in that case, if we look at the sum, at the probability that either A1 happens or A2 happens, that's exactly equal to the sum of the 2 probabilities. Okay, so we'll use these facts here and there throughout the course. So just to be clear, the inequality holds always, but when the two events are disjoint, then in fact we get an equality over here. So let's look at a simple example. Suppose our event A1 is the set of all n-bit strings that happen to end in 1, 1. And suppose A2 is the set of all n-bit strings that happen to begin with 1, 1. Okay, so n, think of it as 8 or some large number. And I'm asking now, what is the probability that either A1 happens or A2 happens? In other words, if I sample uniformly from the universe U, what is the probability that either the least significant bits are 1, 1 or the most significant bits are 1, 1? Well, as we said, that's basically the probability of the union of A1 and A2. We know that the probability of each one of these events is 1/4 by what we just did on the previous slide. And therefore, by the union bound, the probability of the OR is, 1/4, the probability of A1 plus the probability of A2, which is 1/4 plus 1/4. And we just proved that the probability of seeing 1, 1 in the most significant bit or 1, 1 in the least significant bit is less than 1/2. So that's a simple example of how we might go about using the union bound to bound the probability that one of two events might happen. The next concept we need to define is what's called a random variable. Now, random variables are fairly intuitive objects, but unfortunately the formal definition of a random variable can be a little confusing. So what I'll do is I'll give an example, and hopefully that'll be clear enough. So formally, a random variable, denoted say by x, is a function from the universe into some set v. And we say that this set v is where the random variable takes its values. So let's look at a particular example. So suppose we have a random variable x, and this random variable maps into the set 0, 1. So the values of this random variable are going to be either 0 or 1, so 1 bit basically. Now this random variable maps our universe, which is the set of all n-bit binary strings, 0, 1 to the n. And how does it do it? Well, given a particular sample in the universe, a particular n-bit string y, what the random variable will do is simply output the least significant bit of y. And that's it. That's the whole random variable. So now let me ask you, suppose we look at the uniform distribution on the set 0, 1 to the n. Let me ask you, what is the probability that this random variable outputs 0, and what is the probability that the random variable outputs 1? Well, you can see the answers are half and half, but let's just reason through why that's the case. So here we have a picture showing the universe and the possible output space. And so in this case, the variable can output either 0 or 1. Well, when does the variable output 0? The variable outputs 0 when the sample in the universe happens to have its least significant bits be set to 0. And the variable 1 outputs 1 when the sample in the universe happens to have its least significant bit set to 1. Well, if we choose strings uniformly at random, the probability that we choose a string that has its least significant bit set to 0 is exactly 1/2, which is why the random variable outputs 0 with probability exactly 1/2. Similarly, if we choose a random n-bit string, the probability that the least significant bit is equal to 1 is also 1/2, and so we say that the random variable outputs 1 also with exactly probability 1/2. Now, more generally, if we have a random variable taking values in a certain set v, then this random variable actually induces a distribution on the set v. And here I just wrote in symbols what this distribution means, but it's actually very easy to explain. Essentially what it says is that the variable outputs v basically with the same probability that if we sample a random element in the universe and then we apply the function x, we ask how likely is it that the output is actually equal to v. So formally we say that the probability that x outputs v is the same as the probability of the event that when we sample a random element in the universe, we fall into the pre-image of v under the function x. And again, if this wasn't clear, it's not that important. All you need to know is that a random variable takes values in a particular set v and it induces a distribution on that set v. Now, there's a particularly important random variable called a uniform random variable, and it's basically defined as you would expect. So let's say that U is some finite set, for example, the set of all n-bit binary strings, and we're going to denote a random variable R that's basically samples uniformly from the set U by this little funny arrow with a little R on top of it. And this, again, denotes that the random variable R is literally a uniform random variable sampled over the set U. So in symbols, what this means is that for all elements A in the universe, the probability that r is equal to a is simply 1 over u. And if you want to stick to the formal definition of a uniform variable, it's actually not that important. But I'll just say that formally, the uniform random variable is just an identity function, namely rx is equal to x for all x in the universe. So just to see that this is clear, let me ask you a simple puzzle. Suppose we have a uniform random variable over 2-bit strings, so over the sets 0, 0, 0, 1, 1, 0, and 1, 1. And now let's define a new random variable x to basically sum the first and second bits of r. That is, x simply is the sum of r1 and r2, the first and second bits of r, treating those bits as integers. So for example, if r happens to be 0, 0, then x will be 0 plus 0, which is 0. So let me ask you, what is the probability that x is equal to 2? So it's not difficult to see that the answer is exactly 1/4, because basically the only way that x is equal to 2 is if r happens to be 1, 1, but the probability that r is equal to 1, 1 is basically 1/4, because r is uniform over the set of all 2-bit strings. The last concept I want to define in this segment is what's called a randomized algorithm. So I'm sure you're all familiar with deterministic algorithms. These are algorithms that basically take a particular input data as input, and they always produce the same output, say y. So if we run the algorithm 100 times on the same input, we'll always get the same output. So you can think of a deterministic algorithm as a function that, given a particular input data m, will always produce exactly the same output, a of m. A randomized algorithm is a little different in that it, as before, it takes the input data m as input, but it also has an implicit argument called r, where this r is sampled anew every time the algorithm is run. And in particular, this r is sampled uniformly at random from the set of all n-bit strings for some arbitrary n. Now what happens is every time we run the algorithm on a particular input m, we're going to get a different output because a different r is generated every time. So the first time we run the algorithm, we get one output. The second time we run the algorithm, a new r is generated and we get a different output. The third time we run the algorithm, a new r is generated and we get a third output, and so on. So really the way to think about a randomized algorithm is it's actually defining a random variable, right? So given a particular input message m, it's defining a random variable which is defining a distribution over the set of all possible outputs of this algorithm given the input m. So the thing to remember is that the output of a randomized algorithm changes every time you run it, and in fact the algorithm defines a distribution and the set of all possible outputs. So let's look at a particular example. So suppose we have a randomized algorithm that takes as input a message m, and of course it also takes an implicit input, which is this random string that is used to randomize its operation. So now what the algorithm will do is simply it will encrypt the message m using the random string as input. So this basically defines a random variable. This random variable takes values that are encryptions of the message m, and really what this random variable is, it's a distribution over the set of all possible encryptions of the message m under a uniform key. So the main point to remember is that even though the input to a randomized algorithm might always be the same, every time you run the randomized algorithm, you're going to get a different output. Okay, so that concludes this segment, and we'll see a bit more discrete probability in the next segment. In this segment, we're going to continue with a few more tools from discrete probability, and I want to remind everyone that if you want to read more about this, there's more information in this Wikibooks article that is linked over here. So first, let's do a quick recap of where we are. We said that discrete probability is always defined over a finite set, which we're going to denote by u, and typically for us, u is going to be the set of all n-bit binary strings, which we denote by 0, 1 to the n. Now a probability distribution p over this universe u is basically a function that assigns to every element in the universe a weight in the interval 0 to 1, such that if we sum the weight of all these elements, the sum basically sums up to 1. Now we said that a subset of the universe is what's called an event, and we said that the probability of an event is basically the sum of all the weights of the elements in the event. And we said that the probability of an event is some real number in the interval 0 to 1. And I want to remind everyone that basically the probability of the entire universe is basically 1 by the fact that the sum of all the weights sums up to 1. Then we define what a random variable is. Formally, a random variable is a function from the universe to some other set. But the thing that I want you to remember is that the random variable takes values in some set V, and in fact, a random variable defines a distribution on this set V. So the next concept we need is what's called independence, and I'm going to very briefly define this. If you want to read more about independence, please go ahead and look at the Wikibooks article. But essentially, we say that two events A and B are independent of one another if, when you know that event A happens, that tells you nothing about whether event B actually happened or not. Formally, the way we define independence is to say that the probability of A and B, namely that both events happen, is actually equal to the probability of event A times the probability of event B. So multiplication, in some sense, the fact that probabilities multiply under conjunction, captures the fact that these events are independent. And as I said, if you want to read more about that, please take a look at the background material. Now, the same thing can be said for random variables. So suppose we have two random variables, x and y, they take values in some set V. Then we say that these random variables are independent if the probability that x is equal to A and y is equal to B is equal to the product of these two probabilities. Basically, what this means is even if you know that x is equal to A, that tells you nothing about the value of y. Okay, that's what this multiplication means. And again, this needs to hold for all A and B in the space of values of these random variables. So just again, to jog your memory, if you've seen this before, a very quick example. Suppose we look at the set of 2-bit strings, so 0, 0, 0, 1, 1, 0, and 1, 1. And suppose we choose a random element from this set. Okay, so we randomly choose one of these four elements with equal probability. Now let's define two random variables. X is going to be the least significant bit that was generated, and y is going to be the most significant bit that's generated. So I claim that these random variables, x and y, are independent of one another. And the way to see that intuitively is to realize that choosing R uniformly from the set of four elements is basically the same as flipping a coin, an unbiased coin, twice. The first bit corresponds to the outcome of the first flip, and the second bit corresponds to the outcome of the second flip. And of course, there are four possible outcomes. All four outcomes are equally likely, which is why we get the uniform distribution over 2-bit strings. Now, variables x and y, why are they independent? Basically, if I tell you the result of the first flip, namely I tell you the least significant bit of R, so I tell you how the first coin, whether it fell on its head or fell on its tail, that tells you nothing about the result of the second flip. Which is why intuitively you might expect these random variables to be independent of one another. But formally, we would have to prove that for all 0, 1 pairs, the probability of x equals 0 and y equals 0, x equals 1, y equals 1, and so on, these probabilities multiply. Let's just do it for one of these pairs. So let's look at the probability that x is equal to 0 and y is equal to 0. Well, you see that the probability that x is equal to 0 and y is equal to 0 is basically the probability that R is equal to 0, 0. And what's the probability that R is equal to 0, 0? Well, by the uniform distribution, that's basically equal to 1/4. That's 1 over the size of the set, which is 1/4 in this case. And well, lo and behold, that's in fact, these probabilities multiply because, again, the probability that x is equal to 0, the probability that the least significant bit of R is equal to 0, this probability is exactly 1/2, because there are exactly two elements that have their least significant bit equal to 0. 2 out of 4 elements gives you a probability of 1/2. And similarly, the probability that y is equal to 0 is also 1/2, so in fact the probabilities multiply. Okay, so that's this concept of independence. And the reason I wanted to show you that is because we're going to look at an important property of XOR that we're going to use again and again. So before we talk about XOR, let me just do a very quick review of what XOR is. So of course, XOR of 2 bits means the addition of those bits modulo 2. So just to kind of make sure everybody's on the same page, if we have 2 bits, so 0, 0, 0, 1, 1, 0, and 1, 1, their XOR, the truth table of the XOR, is basically just the addition modulo 2. You can see 1 plus 1 is equal to 2, modulo 2, that's equal to 0. So this is the truth table for the XOR, and I'm always going to denote XOR by this circle with a plus inside. And then when I want to apply XOR to bit strings, I apply the addition modulo 2 operation bitwise. So for example, the XOR of these two strings would be 1, 1, 0, and I guess I'll let you fill out the rest of the XORs just to make sure we're all on the same page. So of course it comes out to 1, 1, 0, 1. Now we're going to be doing a lot of XORing in this class. In fact, there's a classical joke that the only thing cryptographers know how to do is just XOR things together. But I want to explain to you why we see XOR so frequently in cryptography. Basically, XOR has a very important property, and the property is the following. Suppose we have a random variable y that's distributed arbitrarily over 0, 1 to the n. So we know nothing about the distribution of y. But now suppose we have an independent random variable that happens to be uniformly distributed also over 0, 1 to the n. So it's very important that x is uniform and that it's independent of y. So now let's define the random variable, which is the XOR of x and y. Then I claim that no matter what distribution y started with, this z is always going to be a uniform random variable. So in other words, if I take an arbitrarily malicious distribution and I XOR it with an independent uniform random variable, what I end up with is a uniform random variable. Okay, and this is again kind of a key property that makes XOR very useful for crypto. So this is actually a very simple fact to prove. Let's just go ahead and do it. Let's just prove it for one bit, so for n equals 1. Okay, so the way we'll do it is we'll basically write out the probability distributions for the various random variables. So let's see, for the random variable y, well, the random variable can be either 0 or 1. And let's say that P0 is the probability that it's equal to 0, and P1 is the probability that it's equal to 1. Okay, so that's one of our tables. Similarly, we're going to have a table for the variable x. Well, the variable x is much easier. That's a uniform random variable, so the probability that it's equal to 0 is exactly 1/2. Probability that it's equal to 1 is also exactly 1/2. Now let's write out the probabilities for the joint distribution. In other words, let's see what the probability is for the various joint values of y and x. In other words, how likely is it that y is 0 and x is 0, y is 0 and x is 1, y is 1 and x is 0, and 1, 1. Well, so what we do is basically, because we assume the variables are independent, all we have to do is multiply the probabilities. So the probability that y is equal to 0 is P0, probability that x is equal to 0 is 1/2, so the probability that we get 0, 0 is exactly P0 over 2. Similarly, for 0, 1, we'll get P0 over 2. For 1, 0, we'll get P1 over 2. And for 1, 1, again, the probability that y is equal to 1 and x is equal to 1, well, that's P1 times the probability that x is equal to 1, which is 1/2, so it's P1 over 2. Okay, so those are the four probabilities for the various options for x and y. So now let's analyze what is the probability that z is equal to 0. Well, the probability that z is equal to 0 is basically the same as the probability that, let's write it this way, xy is equal to 0, 0, or xy is equal to 1, 1. Those are the two possible cases that z is equal to 0 because z is the XOR of x and y. Now these events are disjoint, so this expression can simply be written as the sum of the two expressions given above. So basically it's the probability that xy is equal to 0, 0 plus the probability that xy is equal to 1, 1. So now we can simply look up these probabilities in our table. So the probability that xy is equal to 0, 0 is simply P0 over 2. And the probability that xy is equal to 1, 1 is simply P1 over 2. So we get P0 over 2 plus P1 over 2. But what do we know about P0 and P1? Well, it's a probability distribution. Therefore, P0 plus P1 must equal 1. And therefore, this fraction here must equal to 1/2. P0 plus P1 is equal to 1. So therefore, the sum of these two terms must equal 1/2. And we're done. Basically, we proved that the probability that z is equal to 0 is 1/2. Therefore, the probability that z is equal to 1 is also 1/2. Therefore, z is a uniform random variable. So this simple theorem is the main reason why XOR is so useful in cryptography. The last thing I want to show you about discrete probability is what's called the birthday paradox. And I'm going to do it really fast here because we're going to come back later on and talk about this in more detail. So the birthday paradox says the following. Suppose I choose n random variables in our universe U. Okay, and it just so happens that these variables are independent of one another. They actually don't have to be uniform. All we need to assume is that they're distributed in the same way. The most important property, though, is that they're independent of one another. So the theorem says that if you choose roughly the square root of the size of u elements, we're kind of ignoring this 1.2 here, it doesn't really matter, but if you choose square root of the size of u elements, then basically there's a good chance that there are two elements that are the same. In other words, if you sample about square root of u times, then it's likely that two of your samples will be equal to one another. And by the way, I should point out that this inverted e just means exists. So there exists indices I and j such that Ri is equal to Rj. So here's a concrete example that we'll actually see many, many times. So suppose our universe consists of all strings of length 128 bits. So the size of u is gigantic. It's actually 2 to the 128. It's a very, very large set. But it so happens that if you sample, say, around 2 to the 64 times from the set, this is about the square root of u, then it's very likely that two of your sample messages will actually be the same. So why is this called the birthday paradox? Well, traditionally it's described in terms of people's birthdays, so you would think that each one of these samples would be someone's birthday. And so the question is, how many people need to get together so that there are two people that have the same birthday? So just as a simple calculation, you can see there are 365 days in the year, so you would need about 1.2 times the square root of 365 people until the probability that two of them have the same birthday is more than a half. This, if I'm not mistaken, is about 24, which means that if 24 random people get together in a room, it's very likely that two of them will actually have the same birthday. This is why it's called a paradox, because 24 supposedly is a smaller number than you would expect. Interestingly, people's birthdays are not actually uniform across all 365 days in the year. There's actually a bias towards September, but I guess that's not relevant to the discussion here. The last thing I wanted to do is just show you the birthday paradox a bit more concretely. So suppose we have a universe of about 1 million samples. Then you can see that when we sample roughly 1,200 times, the probability that we sample the same element twice is roughly a half. But the probability of sampling the same number twice actually converges very quickly to 1. You can see that if we sample about 2,200 items, then the probability that two of those items are the same already is 90%. And at 3,000, it's basically 1. So this converges very quickly to 1 as soon as you go beyond the square root of the size of the universe. So we're going to come back and study the birthday paradox in more detail later on, but I just for now wanted you to know what it is. So that's the end of this segment, and then in the next segment we'll start with our first example encryption systems.
Now that we've seen a few examples of historic ciphers, all of which are badly broken, we're going to switch gears and talk about ciphers that are much better designed. But before we do that, I want to first of all define more precisely what a cipher is. So first of all, a cipher is actually, remember, a cipher is made up of two algorithms. There's an encryption algorithm and a decryption algorithm. But in fact, a cipher is defined over a triple. So there's the set of all possible keys, which I'm going to denote by script k. This sometimes I'll call this the key space, the set of all possible keys. There's the set of all possible messages, and the set of all possible ciphertexts. Okay, so this triple, in some sense, defines the environment over which the cipher is defined. And then the cipher itself is a pair of efficient algorithms, E and D. E is the encryption algorithm, D is the decryption algorithm. Of course, E takes keys and messages and outputs ciphertexts. And the decryption algorithm takes keys and ciphertexts and outputs messages. And the only requirement is that these algorithms are consistent. They satisfy what's called a correctness property. So for every message in the message space and every key in the key space, it had better be the case that if I encrypt the message with the key k, and then I decrypt using the same key k, I had better get back the original message that I started with. So this equation here is what's called the consistency equation, and every cipher has to satisfy it in order to be a cipher. Otherwise, it's not possible to decrypt. One thing I wanted to point out is that I put the word efficient here in quotes, and the reason I do that is because efficient means different things to different people. If you're more inclined towards theory, efficient means runs in polynomial time. So algorithms E and D have to run in polynomial time in the size of their inputs. If you're more practically inclined, efficient means runs within a certain time period. So for example, algorithm E might be required to take under a minute to encrypt a gigabyte of data. Either way, the word efficient kind of captures both notions, and you can interpret it in your head whichever way you like. I'm just going to keep referring to it as efficient and put quotes in it. As I said, if you're theory inclined, think of it as polynomial time, and otherwise think of it as concrete time constraints. Another comment I want to make is that in fact algorithm E is often a randomized algorithm. What that means is that as you're encrypting messages, algorithm E is going to generate random bits for itself, and it's going to use those random bits to actually encrypt the messages that are given to it. On the other hand, the decryption algorithm is always deterministic. In other words, given the key and the ciphertext, output is always the same. Doesn't depend on any randomness that's used by the algorithm. Okay, so now that we understand what a cipher is better, I want to kind of show you the first example of a secure cipher. It's called the one-time pad. It was designed by Vernam back at the beginning of the 20th century. Before I actually explain what the cipher is, let's just state it in the terminology that we've just seen. So the message space for the Vernam cipher for the one-time pad is the same as the ciphertext space, which is just the set of all n-bit binary strings. So this just means all sequences of bits of 0, 1 characters. The key space is basically the same as the message space, which is again simply the set of all n-bit binary strings. So a key in the one-time pad is simply a random bit string, so it's a random sequence of bits that's as long as the message to be encrypted, as long as the message. Okay, now that we specified kind of what the cipher is defined over, we can actually specify how the cipher works, and it's actually really simple. So essentially, the ciphertext, which is the result of encrypting a message with a particular key, is simply the XOR of the two, simply K XOR M. So see a quick example of this. Remember that XOR, this plus with a circle, XOR means addition modulo 2. So if I take a particular message, say 0, 1, 1, 0, 1, 1, 1, and I take a particular key, say 1, 0, 1, 1, 0, 0, 1, when I compute the encryption of the message using this key, all I do is I compute the XOR of these two strings. In other words, I do addition modulo 2 bit by bit. So I get 1, 1, 0, 1, 1, 1, 0. That's the ciphertext. And then how do I decrypt? I basically kind of do the same thing. So to decrypt a ciphertext using a particular key, what I do is I XOR the key and the ciphertext again. And so all we have to verify is that it satisfies the consistency requirements. And I'm going to do this slowly once, and then from now on I'm going to assume this is all simple to you. So we're going to have to make sure that if I decrypt a ciphertext that was encrypted using a particular key, I had better get back the message M. So what happens here? Well, let's see. So if I look at the encryption of K and M, this is just K XOR M by definition. What's the decryption of K XOR M using K? That's just K XOR M. And so since I said that XOR is addition modulo 2, addition is associative, so this is the same as K XOR K XOR M, which is simply, as you know, K XOR K is just 0, and 0 XOR anything is simply M. Okay, so this actually shows that the one-time pad is in fact a cipher, but it doesn't say anything about the security of the cipher. And we'll talk about security of the cipher in just a minute. First of all, let me quickly ask you a question just to make sure we're all in sync. Suppose you're given a message M and the encryption of that message using the one-time pad. So all you're given is the message and the ciphertext. My question to you is, given this pair, M and C, can you actually figure out the one-time pad key that was used in the creation of C from M? So I hope all of you realize that, in fact, given the message and the ciphertext, it's very easy to recover what the key is. In particular, the key is simply M XOR C. And we'll see that if it's not immediately obvious to you, we'll see why that's the case a little later in the lecture. Okay. All right. So the one-time pad is really cool from a performance point of view. All you're doing is you're XORing the key and the message. So it's a super, super fast cipher for encrypting and decrypting very long messages. Unfortunately, it's very difficult to use in practice. The reason it's difficult to use is the keys are essentially as long as the message. So if Alice and Bob want to communicate securely, so Alice wants to send a message M to Bob, before she begins even sending the first bit of the message, she has to transmit a key to Bob that's as long as that message. Well, if she has a way to transmit a secure key to Bob that's as long as the message, she might as well use that same mechanism to also transmit the message itself. So the fact that the key is as long as the message is quite problematic and makes the one-time pad very difficult to use in practice. Although we'll see that the idea behind the one-time pad is actually quite useful. And we'll see that a little bit later. But for now, I want to focus a little bit on security. So the obvious questions are, why is the one-time pad secure? Why is it a good cipher? Then to answer that question, the first thing we have to answer is, what is a secure cipher to begin with? What is it? What makes a cipher secure? Okay, so to study security of ciphers, we have to talk a little bit about information theory. And in fact, the first person to study security of ciphers rigorously is a very famous, the father of information theory, Claude Shannon, and he published a famous paper back in 1949 where he analyzes the security of the one-time pad. So the idea behind Shannon's definition of security is the following. Basically, if all you get to see is the ciphertext, then you should learn absolutely nothing about the plaintext. In other words, the ciphertext should reveal no information about the plaintext. And you see why it took someone who invented information theory to come up with this notion, because he had to formally explain what does information about the plaintext actually mean. Okay? So that's what Shannon did. And so let me show you Shannon's definition. I'll write it out slowly first. So what Shannon said is, suppose we have a cipher ED that's defined over a triple KMNC just as before. So KMNC define the key space, the message space, and the ciphertext space. And we say that the cipher has perfect secrecy if the following condition holds. It so happens that for every two messages, M0 and M1 in the message space, for every two messages, the only requirement I'm going to put on these messages is they have the same length. So we'll see why this requirement is necessary in just a minute. And for every ciphertext in the ciphertext space, okay, so for every pair of messages and for every ciphertext, it had better be the case that if I ask, what is the probability that encrypting M0 with K, encrypting M0 with K gives C, okay, so how likely is it, if we pick a random key, how likely is it that when we encrypt M0 we get C? That probability should be the same as when we encrypt M1. Okay, so the probability of encrypting M1 and getting C is exactly the same as the probability of encrypting M0 and getting C. And this is, as I said, where the key, the distribution, is over the distribution on the key. So the key is uniform in the key space. So K is uniform in K. And I'm often going to write K arrow with a little r above it to denote the fact that K is a random variable that's uniformly sampled in the key space K. Okay, this is the main part of Shannon's definition. And let's think a little bit about what this definition actually says. So what does it mean that these two probabilities are the same? Well, what it says is that if I'm an attacker and I intercept a particular ciphertext C, then in reality, the ciphertext, the probability that the ciphertext is the encryption of M0 is exactly the same as the probability that it's the encryption of M1, because those probabilities are equal. So if all I have is the ciphertext C, that's all I've intercepted, I have no idea whether the ciphertext came from M0 or the ciphertext came from M1, because again, the probability of getting C is equally likely whether M0 is being encrypted or M1 is being encrypted. So here we have the definition stated again, and I just want to write these properties again more precisely. So let's write this again. So what this definition means is that if I'm given a particular ciphertext, I can't tell where it came from. I can't tell if the message that was encrypted is either M0 or M1. And in fact, this property is true for all messages, for all these M0, for all M0 and M1. So not only can I not tell if C came from M0 or M1, I can't tell if it came from M2 or M3 or M4 or M5, because all of them are equally likely to produce the ciphertext C. So what this means really is that if you're encrypting messages with a one-time pad, then in fact the most powerful adversary, I don't really care how smart you are, the most powerful adversary can learn nothing about the plaintext, learns nothing about the plaintext from the ciphertext. So just to say it in one more way, basically what this proves is that there's no ciphertext only attack on a cipher that has perfect secrecy. Now, ciphertext only attacks actually aren't the only attacks possible, and in fact, other attacks may be possible. But other attacks may be possible. Okay. Now that we understand what perfect secrecy means, the question is, can we build ciphers that actually have perfect secrecy? And it turns out we don't have to look very far. The one-time pad, in fact, has perfect secrecy. So I want to prove to you, this is Shannon's first results, and I want to prove this fact to you. It's a very simple proof, so let's go ahead and look at it and just do it. So we need to kind of interpret, what does it mean? What is this probability that ek of m0 is equal to c? So it's actually not that hard to see that for every message in every ciphertext, the probability that the encryption of m under a key k, the probability that that's equal to c, the probability of a random choice of key, by definition, all that is basically the number of keys, k in script k, such that, well, if I encrypt m with k, I get c. So I literally count the number of such keys, and I divide by the total number of keys. Right? That's what it means that if I choose a random key, that key maps m to c. Right? So it's basically the number of keys that map m to c divided by the total number of keys. This is this probability. So now suppose that we had a cipher such that for all messages in all ciphertext, it so happens that if I look at this number, the number of k in k, such that ekm is equal to c. In other words, I'm looking at the number of keys that map m to c. Suppose this number happens to be a constant. So say it happens to be 2, 3, or 10, or 15. It just happens to be an absolute constant. If that's the case, then by definition, for all m0 and m1, and for all c, this probability has to be the same, because the denominator is the same, the numerator is the same, it's just this constant, and therefore this probability is always the same for all m and c. And so if this property is true, then the cipher has perfect secrecy. Okay, so let's see what can we say about this quantity for the one-time pad. So the question to you is, if I have a message in a ciphertext, how many one-time pad keys are there that map this message m to the ciphertext c? In other words, how many keys are there such that m XOR k is equal to c? So I hope you've all answered 1, and let's see why that's the case. For the one-time pad, if we have that the encryption of k of m under k is equal to c, that basically, well, by definition, that implies that k XOR m is equal to c. But that also simply says that k has to be equal to m XOR c. Yes, I just XOR both sides by m, and I get that k must equal to m XOR c. Okay, so what that says is that for the one-time pad, in fact, the number of keys in k such that ekm is equal to c, that simply is 1, and this holds for all messages and ciphertext. And so again, by what we said before, this says that the one-time pad has perfect secrecy. Perfect secrecy, and that completes the proof of this trivial, very, very simple lemma. Now, the funny thing is that even though this lemma is so simple to prove, in fact, it proves a pretty powerful statement again. This basically says, for the one-time pad, there is no ciphertext-only attack. So unlike the substitution cipher, or the Vigenère cipher, or the rotor machines, all those could be broken by ciphertext-only attack, we've just proved that for the one-time pad, that's simply impossible. Given the ciphertext, you simply learn nothing about the plaintext. However, as we'll see, this is not the end of the story. I mean, are we done? I mean, basically, we're done with the course now, because we have a way to encrypt so that an attacker can't recover anything about our message. So maybe we're done with the course. But in fact, as we'll see, there are other attacks. And in fact, the one-time pad is actually not such a secure cipher. In fact, there are other attacks that are possible, and we'll see that shortly. Okay? So I emphasize again, the fact that it has perfect secrecy does not mean that the one-time pad is a secure cipher to use. Okay, but as we said, the problem with the one-time pad is that the secret key is really long. So if you had a way of communicating the secret key over to the other side, you might as well use that exact same method to also communicate the message to the other side, in which case you wouldn't need a cipher to begin with. Okay, so the problem again is the one-time pad has really long keys, and so the obvious question is, are there other ciphers that have perfect secrecy and possibly have much, much shorter keys? Well, so the bad news is that Shannon, after proving that the one-time pad has perfect secrecy, proved another theorem that says that if in fact a cipher has perfect secrecy, the number of keys in a cipher must be at least the number of messages that the cipher can handle. Okay, so in particular what this means is if I have perfect secrecy, then necessarily the number of keys, or rather the length of my key, must be greater than the length of the message. So in fact, since the one-time pad satisfies this with equality, the one-time pad is an optimal cipher that has perfect secrecy. Okay, so basically what this shows is that this is an interesting notion. The one-time pad is an interesting cipher, but in fact, in reality, it's actually quite hard to use. Hard to use in practice, again, because of these long keys. And so this notion of perfect secrecy, even though it's quite interesting, basically says that it doesn't really tell us that practical ciphers are going to be secure. And we're going to see, but as we said, the idea behind the one-time pad is quite good, and we're going to see in the next lecture how to make that into a practical system.
Now that we know about the one-time pad, let's talk about making the one-time pad more practical using something called the stream cipher. But before we do that, let's do a quick review of where we were. So let me just remind you that a cipher is defined over a triple of sets called a key space, a message space, and a ciphertext space. And a cipher is a pair of efficient algorithms called E and D. E stands for encryption and D stands for decryption. And the only property that we need to satisfy is that decryption is the opposite of encryption. In other words, if I encrypt a message M using a particular key and I decrypt using the same key, I get back the original message. Last time we looked at a couple of weak ciphers like the substitution cipher and the Vigenère cipher. We showed that all of them can be easily broken, so you should never, ever, ever use those ciphers. Those were just for historical reference. And then we looked at our first example of a good cipher, namely the one-time pad. Let me just remind you how the one-time pad is defined. Basically, the message space is the set of all n-bit strings. The ciphertext is the set of all n-bit strings, and similarly, the key is the set of all n-bit strings. And the way we encrypt is by a simple XOR. To encrypt the message, we just XOR the message and the key. That gives us the ciphertext. And then to decrypt the ciphertext, we just do this XOR again. And it's easy to show by properties of XOR that, in fact, decryption is the opposite of encryption. And then we talked about this lemma. In fact, we proved it. That says that the one-time pad has perfect secrecy, which means that if you're just an eavesdropper and you just get to see a single ciphertext, you're not going to be able to deduce any information about the encrypted plaintext. Unfortunately, we also said that Shannon proved this lemma. We called it the bad news lemma, that basically says that any cipher that has perfect secrecy must have really long keys. In other words, the key length must be at least as long as the length of the message, which means that the cipher is not particularly useful, because if two parties have a way to agree on really long keys that are as long as the message, they, in some sense, might as well use that mechanism to already transmit the message itself. So in this lecture, we're going to take the idea of the one-time pad and try to make it into a practical encryption scheme. So this is what's called a stream cipher. So the idea in a stream cipher is, rather than using a totally random key, we're actually going to use a pseudo-random key. And to explain how that works, I need to define what is a pseudo-random generator, a PRG. So a PRG, really, all it is just a function, and I'll call it G for generator, that takes a seed. So I'm going to use 0, 1 to the s to denote all strings of length s. So this we'll call the seed space. So it takes an s-bit seed and maps it into a much larger string, which we'll denote by 0, 1 to the n. And the property is that n must be much, much larger than s. So in other words, we take a seed that might be maybe only 128 bits, and we expand it into a much, much larger output string that could be gigabytes long. That's what this pseudo-random generator does. And of course, the goal is that, first of all, the generator is efficiently computable. So the function g, there should be some sort of an efficient algorithm that computes it. So efficiently computable by a deterministic algorithm. It's important to understand that the function g itself has no more randomness in it. It's totally deterministic. The only thing that's random here is the random seed that's given as input to the function g. And the other property, of course, is that the output should look random. And the question is, what does it mean to look random? And that's something that we'll define later on in the lecture. Okay, so suppose we have such a generator. How do we use that to build a stream cipher? Well, the idea is that we're going to use the seed as our key. So our short seed is going to be the secret key. And then we're going to use the generator to basically expand the seed into a much, much larger random-looking sequence, or pseudo-random sequence, as it's known. So this would be g of k. And then we are going to XOR it, just like in the one-time pad. We're going to XOR the pseudo-random sequence with the message, and that's going to give us the ciphertext. Or if we want to write this in math, we'll write C equals the encryption of the message M with a key K, which is simply defined as M XOR G of K. And then when we want to decrypt, basically we do exactly the same thing. It's basically the ciphertext XOR G of K, just like in the one-time pad, except that instead of XORing with K, we XOR with the output of the generator applied to K. So the first question to ask is, why is this secure? So basically, we only have one notion of security so far, which we called perfect secrecy. And so let's just quickly ask, can a stream cipher have perfect secrecy? Remember, in the stream cipher, the key is much, much shorter than the message. And so nevertheless, can it have perfect secrecy? So I hope everybody said the answer is no. The key is much shorter than the message, and we said that in a perfectly secure cipher, the key must be as long as the message, and therefore it's not possible that a stream cipher actually has perfect secrecy. So the question is then, well, why is it secure? First of all, we would need a different definition of security to argue that the stream cipher is secure, and in particular, the security property is going to depend on the specific generator that we used. So in fact, the definition of privacy that we'll need to argue security of stream ciphers we'll see in the next lecture. But for now, let me show you one particular property that a generator must have, a minimal property needed for security. This property is called unpredictability. So let's just suppose for 1 second that in fact a stream cipher is predictable. So what does that mean? Suppose the PRG is predictable. What that means is essentially that there is some I such that if I give you the first I bits of the output, this notation, bar 1 to I, means look at the first I bits of the output of the function. Okay, so I give you the first I bits of the stream. There is some sort of an algorithm, there's an efficient algorithm that will compute the rest of the stream. Okay, so given the first I bits, you can compute the remainder of the bits. I claim that if this is the case, then the stream cipher would not be secure. So let's see why. Well, suppose an attacker actually intercepts a particular ciphertext, let's call it C. Right, if this is the case, then in fact we have a problem. Because suppose that just by some prior knowledge, the attacker actually knows that the initial part of the message happens to be some known value. For example, you know that in the mail protocol, SMTP, the standard send mail protocol used in the internet, you know that every message starts with a word from colon. Well, that would be a prefix that the adversary knows that the message must begin with, from colon. What it could do is it could XOR the ciphertext with the words from colon, with the little prefix of the message that it actually knows, and what that would give it is a prefix of the pseudo-random sequence. So now it would learn as a result of this, it would learn a prefix of the pseudo-random sequence. But then we know that once it has a prefix of the pseudo-random sequence, it can predict the remainder of the pseudo-random sequence, and that would allow it to then predict the rest of the message M. Okay, so for example, if the pseudo-random generator was predictable given 5 bits of the pad, then every email encrypted using the stream cipher would be decryptable because, again, the attacker knows the prefix of the message, from which he deduces a prefix of the pad, which then allows him to compute the rest of the pad, which then allows him to recover the entire plaintext. Okay, so this is an example that shows that in fact if a PRG is predictable, then already there are security problems because a small prefix would reveal the entire message. As it turns out, even if I could just predict one bit of the output, even if given the first I bits, I can predict the next bit, the I plus first bit, already this is a problem, because that would say that given, again, the first couple of letters in a message, I can decrypt essentially and recover the next bit of the message, or the next letter of the message, and so on. So this predictability property shows that, if we use a PRG that's going to be used in a stream cipher, it had better be unpredictable. So what does it mean that a PRG is unpredictable? So let's define more precisely what it means for a PRG to be unpredictable. Well, first we'll define more precisely what it means for a PRG to be predictable. So we say that G is predictable if there exists an efficient algorithm, let's call it A, and there is some position, there's a position I between 1 and n minus 1, such that if we look at the probability over a random key, probability that if I generate a random key, and remember this notation means choose a random key from the set K, so this arrow with R just means choose a random key from the set K. Basically, if I give this algorithm the prefix of the output, so I give it the first I bits of the output, the probability that it's able to predict the next bit of the output, this probability is greater than half plus epsilon for some non-negligible epsilon. And non-negligible, for example, would be epsilon which is greater than 1 over 2 to the 30. 1 over a billion, for example, we would consider non-negligible. So these terms, negligible and non-negligible, we'll come back at the end of the lecture and define them more precisely. But for now, let's just stick with the intuitive notion of what non-negligible means. And so this is what it means for an algorithm, for a generator to be predictable. Basically, there's some algorithm that is able to predict the I plus first bit, even the initial prefix. Okay? And then we say that an algorithm, that a PRG is unpredictable if in fact, if it doesn't satisfy the property that we just defined. In other words, it is not predictable. But what does it mean more precisely for it not to be predictable? It means that in fact for all positions, for all I, there's no efficient adversary, no efficient algorithm A that can predict the I plus first bit with non-negligible probability epsilon. Okay, and this has to be true for all I. So no matter which prefix I give you, you're not going to be able to predict the next bit that follows the prefix. Okay, so let's look at some examples. Here's a silly example. Suppose I give you a generator and I ask you, is it predictable? Well, this generator happens to have the property that if I XOR all the bits of the output, I always happen to get 1. Okay, so I XOR all the bits, bit number 1, XOR bit number 2, XOR bit number 3. If I XOR all those bits, I happen to get 1. The question is that a predictable generator? And again, I hope everybody answered yes, that essentially given the first n minus 1 bits of the output, I can predict the nth bit because it would just be the bit that's needed to make the XOR of all the bits be 1. In other words, if I give you all but one of the bits of the generator, you can actually predict the last bit of the generator. Now that we've seen that PRGs have to be unpredictable, I just want to mention a couple of weak PRGs that should never ever be used for crypto. This is a very common mistake, and I just want to make sure none of you guys make this mistake. So a very common PRG that should actually never be used for crypto is called a linear congruential generator. So let me explain what a linear congruential generator is. Basically, it has parameters. It has 3 parameters. I'll call them A, B, and P. A and B are just integers, and P is a prime. And the generator is defined as follows. Essentially, I'll say R0 is the seed of the generator. And then the way you generate randomness is basically you iteratively run through the following steps. You compute A times R of I minus 1 plus B modulo P. Then you output a few bits of the current states, output few bits of Ri. Then, of course, you increment I, and you iterate this again and again and again. Okay, so you can see how this generator proceeds. It starts with a particular seed. At every step, there is this linear transformation that's being applied to the seed, and then you output a few bits of the current state, and then you do that again and again and again and again. Unfortunately, even though this generator has good statistical properties in the sense that, for example, the number of zeros it outputs is likely going to be similar to the number of ones and so on. You can actually argue all sorts of nice statistical properties about this. Nevertheless, it is a very easy generator to predict, and in fact should never ever be used. In fact, just given a few output samples, it's easy to predict the remainder of the sequence. And as a result, this generator should never ever be used. Another example is a random number generator that's very closely related to the linear congruential generator. This is a random number generator implemented in glibc, very common library, that you can see. I just wrote down the definition here. You can see that it basically outputs a few bits at every iteration, and it just does this simple linear transformation at every step. Again, this is a very easy generator to predict and should never ever be used for crypto. And so kind of the lesson I want to just emphasize here is never ever use the function, the built-in glibc function random for crypto, because it doesn't produce cryptographic randomness in the sense that it's easy to predict. And in fact, systems like Kerberos version 4 have used random and have been bitten by that. So please don't make that mistake yourself. We'll talk about how to do secure random number generation actually in the next lecture. Before we conclude this lecture, I just want to give a little bit more detail about these concepts of negligible and non-negligible values. So different communities in crypto actually define these concepts differently. For practitioners, basically the terms negligible and non-negligible are just particular scalars that are used in the definition. So for example, a practitioner would say that if a value is more than 1 over a billion, 1 over 2 to the 30, we say that the value is non-negligible. The reason that's so is because if you happen to use a key, for example, for encrypting a gigabyte of data is about 2 to the 30, or maybe even 2 to the 32 bytes, then an event that happens with probability 1 over 2 to the 30 will likely happen after about a gigabyte of data. So since a gigabyte of data is within reason for a particular key, this event is likely to happen. Therefore, 1 over 2 to the 30 is non-negligible. On the other hand, we'll say that 1 over 2 to the 80, which is much, much, much smaller, is an event that happens with this probability, is an event that's actually not going to happen over the life of the key, and therefore we'll say that that's a negligible event. As it turns out, these practical definitions of negligible and non-negligible are quite problematic, and we'll see examples of why they're problematic later on. So in fact, in the more rigorous theory of cryptography, the definition of negligible and non-negligible are somewhat different. And in fact, when we talk about the probability of events, we don't talk about these probabilities as scalars, but rather we talk about them as functions of a security parameter. So let me explain what that means. So these functions are essentially functions that output positive real values, or non-negative real values that are supposedly probabilities, but they're functions that act on non-negative integers. Okay, so what does it mean for a function to be non-negligible? What it means is that the function is bigger than some polynomial infinitely often. In other words, for infinitely many values, the function is bigger than some 1 over polynomial. Okay, so I wrote the exact definition here, and we'll see an example in just a minute. Okay, so if something is often bigger than 1 over a polynomial, we'll say that it's not negligible. However, if something is smaller than all polynomials, then we'll say that it's negligible. So what this says here is basically for any degree polynomial, for all d, there exists some lower bound lambda d such that for all lambda bigger than this lambda d, the function is smaller than 1 over the polynomial. Okay, so all this says is that the function is negligible if it's less than all polynomial fractions. In other words, it's less than 1 over lambda d for sufficiently large lambda. So let's look at some examples, and we'll see applications of these negligible and non-negligible concepts later on, but I just wanted to make it clear that this is how you would rigorously define these concepts. Basically, either smaller than 1 over poly or bigger than 1 over poly. One would be negligible, the other would be non-negligible. So let's look at some examples. So for example, a function that drops exponentially in lambda clearly would be negligible because for any constant d, there is a sufficiently large lambda such that 1 over 2 to the lambda is less than 1 over lambda to the d. Okay, so this is clearly less than all polynomials. However, the function, say, 1 over lambda to 1,000, right? This is a function that grows very, very, very slowly. It barely ever moves. Nevertheless, this function is non-negligible because if I set d to be 10,000, then clearly this function is bigger than 1 over lambda to the 10,000. And so this function is bigger than some polynomial fraction. Now let's look at a confusing example, just to be tricky. What do you think? Suppose I have a function that for odd lambda happens to be exponentially small, for even lambda happens to be polynomially small. Is this a negligible or non-negligible function? Well, by our definition, this would be a non-negligible function. And the intuition is if a function happens to be only polynomially small very often, that actually means that this event, an event that happens with this probability, is already too large to be used in a real crypto system. Okay, so the main points to remember here are that these terms basically correspond to less than polynomial or more than polynomial. But throughout the course, we'll mostly use negligible to mean less than an exponential, and non-negligible to mean less than 1 over polynomial. So now we saw the core idea for converting the one-time pad into a practical cipher, namely a stream cipher. And then in the next lecture, we're going to see how to actually argue that the stream cipher is actually secure. That's going to require a new definition of security, since perfect secrecy is not good enough here. And we will see that in the next lecture. In this segment, we're going to look at attacks on the one-time pad and some things you need to be careful with when you use the stream cipher. But before we do that, let's do a quick review of where we were. So recall that the one-time pad encrypts messages by XORing the message and a secret key, where the secret key is as long as the message. Similarly, decryption is done by similarly XORing the ciphertext and the same secret key. When the key is uniform and random, we prove that the one-time pad has this information theoretic security that Shannon called perfect secrecy. The problem was, of course, the keys are as long as the message, so the one-time pad is very difficult to use. We then talked about a way to make the one-time pad practical by using a pseudo-random generator that expands a short seed into a much larger message. And the way a stream cipher worked, essentially using a pseudo-random generator, was in the same way as the one-time pad, basically, but rather than using a truly random pad, we used the pseudo-random pad that's expanded to be as long as the message from the short key that's given as input to the generator. We said now that security no longer relies on perfect secrecy because stream ciphers cannot be perfectly secure. Instead, security relies on properties of the pseudorandom generator. And we said that the pseudorandom generator essentially needs to be unpredictable. But in fact, it turns out that definition is a little bit hard to work with. And we're going to see a better definition of security for PRGs in about 2 segments. But in this segment, we're going to talk about attacks on the one-time pad. And the first attack I want to talk about is what's called the two-time pad attack. Okay, so remember that the one-time pad is called one-time pad because the pad can only be used to encrypt a single message. I want to show you that if the same pad is used to encrypt more than one message, then security goes out the window and basically an eavesdropper can completely decrypt encrypted messages. So let's look at an example. So here we have 2 messages, M1 and M2, that are encrypted using the same pad. So the resulting ciphertext, C1 and C2, again, basically are encryptions of these messages, M1 and M2, but both are encrypted using the same pad. Now suppose an eavesdropper intercepts C1 and C2, and he basically has both C1 and C2. The natural thing for the eavesdropper to do is actually compute the XOR of C1 and C2, and what does he get when he computes this XOR? So I hope everybody sees that basically once you XOR C1 and C2, the pads cancel out, and essentially what comes out of this is the XOR of the plaintext messages. And it turns out that English basically has enough redundancy such that if I give you the XOR of 2 plaintext messages, you can actually recover those 2 messages completely. More importantly for us, since these messages are encoded using ASCII, in fact, ASCII encoding has enough redundancy such that given the XOR of 2 ASCII encoded messages, you can recover the original messages back. Okay, so essentially given these XORs, you can recover both messages. So the thing to remember here is if you ever use the same pad to encrypt multiple messages, an attacker who intercepts the resulting ciphertexts can basically recover the original plaintexts without too much work. So the stream cipher key or the one-time pad key should never, ever, ever, ever be used more than once. So let's look at some examples where this comes up in practice. It's a very common mistake to use a stream cipher key or a one-time pad key more than once. And let me show you some example where this comes up so you know to avoid these mistakes when you build your own systems. The first example is a historic example at the beginning of the 1940s where the Russians actually used a one-time pad to encrypt various messages. Unfortunately, the pads that they were using were generated by a human by throwing dice. And so, the human would throw these dice and write down the results of these throws, and the collected throws would then form the pads that were used for encryption. Now, because it was kind of laborious for them to generate these pads, it seemed wasteful to use the pad to encrypt just one message, so they ended up using these pads to encrypt multiple messages. And US intelligence was actually able to intercept these two-time pads, these ciphertexts that were encrypted using the same pad applied to different messages. And it turns out over a period of several years, they were able to decrypt something like 3,000 plaintexts just by intercepting these ciphertexts. The project is called Project Venona. It's actually a fascinating story of cryptanalysis just because the two-time pad is insecure. More importantly, I want to talk about more recent examples that come up in networking protocols. So let me give you an example from Windows NT in a protocol called the point-to-point transfer protocol. This is a protocol for a client wishing to communicate securely with a server. The client and the server both share a secret key here, and they both send messages to one another. So here we'll denote the messages from the client by M1. So the client sends a message, the server responds, the client sends a message, the server responds, the client sends a message, the server responds, and so on and so forth. Now, the way PTP works is basically the entire interaction from the client to the server is considered as one stream. In other words, what happens is the messages M1 and M2 and M3 are kind of viewed as one long stream. Here, these two parallel lines means concatenation. So essentially, we're concatenating all the messages from the client to the server into one long stream, and all that stream is encrypted using the stream cipher with key K. So that's perfectly fine. I mean, there's nothing wrong with that. These messages are encrypted, are treated as one long stream, and they're all encrypted using the same key. The problem is the same thing is happening also on the server side. In other words, all the messages from the server are also treated as one long stream. So here, they're all concatenated together and encrypted using, unfortunately, the same pseudo-random seed. In other words, using the same stream cipher key. So basically what's happening here is you see an effect that the two-time pad is taking place where the set of messages from the client is encrypted using the same one-time pad as the set of messages from the server. The lesson here is that you should never use the same key to encrypt traffic in both directions. In fact, what you need to do is to have one key for interaction between the client and the server and one key for interaction between the server and the client. The way I like to write this is really that the shared key K really is a pair of keys. One key is used to encrypt messages from server to client, and one key is used to encrypt messages from client to server. So these are two separate keys that are used, and both sides, of course, know this key. So both sides have this pair of keys. Okay, and they can both encrypt. So one is used to encrypt messages in one direction, and the other is used to encrypt messages in the other direction. So another important example of the two-time pad comes up in Wi-Fi communication, in particular in the 802.11b protocol. So all of you, I'm sure, know that 802.11 contains an encryption layer, and the original encryption layer was called WEP. And WEP, fortunately for us, is actually a very badly designed protocol, so that I can always use it as an example of how not to do things. There are many, many mistakes inside of WEP, and here I want to use it as an example of how the two-time pad came about. So let me explain how WEP works. So in WEP, there's a client and an access point. Here's the client, here's the access point. They both share a secret key K. And then when they want to transmit a message to one another, say these are frames that they transmit to one another. Let's say the client wants to send a frame containing the plaintext M to the access point. What he would do is first of all, he appends some sort of a checksum to this plaintext. The checksum is not important at this point. What is important is that then this concatenation gets encrypted using a stream cipher, where the stream cipher key is this concatenation of a value IV and a long-term key K. So this IV is a 24-bit string. Okay, this IV is a 24-bit string. And you can imagine that it starts from 0, and perhaps it's a counter that counts increments by 1 for every packet. The reason they did this is the designers of WEP realized that in a stream cipher, the key is only supposed to be used to encrypt one message. And so they said, well, let's go ahead and change the key after every frame. And the way they changed the key essentially was by prepending this IV to it. And you notice this IV changes on every packet, so it increments by 1 on every packet. And the IV then is sent in the clear along with the ciphertext. So the recipient knows the key K, he knows what the IV is, he can rederive the PRG of IV concatenated K, and then decrypt the ciphertext to recover the original message M. Now the problem with this, of course, is the IV is only 24 bits long, which means that there are only 2 to the 24 possible IVs, which means that after 16 million frames are transmitted, essentially the IV has to cycle. And once it cycles, after 60 million frames, essentially we get a 2-time pad. The same IV would be used to encrypt 2 different messages. The key K never changes. It's a long-term key. And as a result, the same key, namely IV concatenated K, would be used to encrypt 2 different frames, and the attacker can then figure out plaintext of both frames. So that's one problem. And the worst problem is, in fact, that on many 802.11 cards, if you power cycle the card, the IV will reset back to 0. And as a result, every time you power cycle the card, essentially you'll be encrypting the next payload using 0 concatenated K. So after every power cycle, you'll be using the 0 concatenated K key to encrypt many, many, many times the same packet. So you see how in WEP, the same pad could be used to encrypt many different messages as soon as the IV is repeated. There's nothing to prevent the IV from repeating after a power cycle or from repeating after every 16 million frames, which isn't that many frames in a busy network. So while we're talking about WEP, I want to mention one more mistake that was done in WEP. This is a pretty significant mistake, and let's see how we might design it better. So you notice that the designers of WEP basically wanted to use a different key for every packet. Okay, so every frame is encrypted using a different key, this concatenation of IV and K. Unfortunately, they didn't randomize the keys, and the keys are actually, if you look at the key for frame number 1, well, it'll be this concatenation of 1 and K. This field is 24 bits. And then the key for frame number 2 is the concatenation of 2 and K. The key for frame number 3 is the concatenation of 3 and K. So the keys are very closely related to one another. And I should probably mention also that these keys themselves can be 104 bits, so that the resulting PRG key is actually 104 plus 24 bits, which is 128 bits. Unfortunately, these keys are very much related to one another. These are not random keys. You notice they all have the same suffix of 104 bits. And it turns out the pseudorandom generator used in WEP is not designed to be secure when you use related keys that are so closely related. In other words, the majority of these keys are basically the same. And in fact, for the PRG that's used in WEP, that PRG is called RC4. We'll talk about that more in the next segment. It turns out there's an attack that was discovered by Fleurer, Mantin, and Shamir back in 2001 that shows that after about 10 to the 6, after about 1 million frames, you can recover the secret key, can recover K. So this is kind of a disastrous attack that says essentially all you have to do is listen to about 1 million frames. These frames basically, as we said, they're all generated from a very common seed, namely 104 bits of these seeds are all the same. The fact that you've used such closely related keys is enough to actually recover the original key. And it turns out even after the 2001 attack, better attacks have come out that show that these related keys are very much disastrous, and in fact these days something like 40,000 frames are sufficient, and so that within a matter of minutes you can actually recover the secret key in any WEP network. So WEP provides no security at all for 2 reasons. First of all, it can result in a 2-time pad, but more significantly, because these keys are so closely related, it's actually possible to recover the key by watching just a few ciphertexts. And by the way, we'll see that when we do a security analysis of these types of constructions, in a few segments we'll start talking about how to analyze these types of constructions. We'll see that when we have related keys like this, in fact, our security analysis will fail. We won't be able to get the proof to go through. So one could ask, what should the designers of web should have done instead? Well, one approach is to basically treat the frames, M1, M2, M3. Each one is a separate frame transmitted from the client to the server. They could have treated them as one long stream and then XOR them essentially using the pseudo-random generator as one long stream. So the first segment of the pad would have been used to encrypt M1. The second segment of the pad would have been used to encrypt M2. The third segment of the pad would have been used to encrypt M3, and so on and so forth. So they basically would never have had to change the key because the entire interaction is viewed as one long stream. But they chose to have a different key for every frame. So if you want to do that, a better way to do that is rather than slightly modifying this IV that just slightly modifies the prefix of the key, of the PRG key, a better way to do that is to use a PRG again. So essentially what you could do is you would take your long-term key and then feed that directly through a PRG. So now we get a long stream of bits that look essentially random. And then the initial segment could be used, the first segment could be used as the key for frame number 1. And then the second segment would be used as the key for, key from frame number 2, and so on and so forth. The third segment would be used to encrypt frame number 3, and so on and so forth. Okay? So the nice thing about this is now essentially by doing this, each frame has a pseudo-random key. These keys now have no relation to one another. They look like random keys. And as a result, if the PRG is secure for random seeds, it would also be secure on this input because these keys essentially look as though they're independent of one another. We'll see how to do this analysis formally once we talk about these types of constructions. Since this two-time pad attack comes up so often in practice, it's such a common mistake, I want to give one more example where it comes up so you know how to avoid it. And the last example I want to give is in the context of disk encryption. So imagine we have a certain file, and maybe the file begins with, the words to Bob. And then the contents of the file follows. When this is stored on disk, of course, the file is going to get, so here we have our disk here. The file is going to get broken into blocks. And each block will be, when we actually store this on disk, things will be encrypted. And, so maybe to Bob will go into the first block, and then the rest of the content will go into the remaining blocks. But of course, this is all encrypted, so I'll kind of use these lines here to denote the fact that this is encrypted, and an attacker looking at the disk has no idea what the contents of the message is. But now suppose that at a later time, user goes ahead and modifies, basically, fires up the editor and modifies the file. So now instead of saying to Bob, it says to Eve, and nothing else changes in the file. That's the only change that was made. When the user then saves this modified file to disk, basically he's going to re-encrypt it again. And so the same thing is going to happen. The file is going to get broken into blocks. Now the file is going to say to Eve, and everything, of course, is going to be encrypted. So again, I'll put these lines here. Now, an attacker looking at the disk, taking a snapshot of the disk before the edit, and then looking again at the disk after the edit, what he will see is that the only thing that changed is this little segment here that's now different. Everything else looks exactly the same. So the attacker, even though he doesn't know what actually happened to the file, what's in the file, or what changed, he knows exactly the location where the edit took place. And so the fact that the one-time pad or a stream cipher encrypts one bit at a time means that if one change takes place, then it's very easy to tell where that change occurred. And that leaks information that the attacker shouldn't actually learn. Ideally, you'd like to say that even if the file changed just a little bit, the entire contents of the file should change, or maybe at least the entire contents of the blocks should change. Here you can see that the attacker even knows within the block where the change was actually made. Okay, so in fact, because of this, it's usually a bad idea to use stream ciphers for disk encryption. And essentially, this is another example of a two-time pad attack because the same pad is used to encrypt two different messages. They happen to be very similar, but nevertheless, these are two different messages, and the attacker can learn what the change was. And in fact, he might be able to even learn what the actual changed words were as a result of this. Okay, so the lesson here is generally we need to do something different for disk encryption. We'll talk about what to do for disk encryption in a later segment, but essentially the one-time pad is generally not a good idea for encrypting blocks on disk. So just again, to summarize the two-time pad attack, we saw that you're supposed, I hope I've convinced you that you're never, ever, ever supposed to use a stream cipher key more than once. Even though there are natural settings where that might happen, you have to take care and make sure that you're not using the same key more than once. So for network traffic, typically what you're supposed to do is every session would have its own key. Within the session, the message from the client to the server would look as one complete stream. It would be encrypted using one key. The messages from the server to the client would be treated as one stream and encrypted using a different key. And then for disk encryption, typically you would not use a stream cipher because as changes are made to the file, you would be leaking information about the contents of the file. Okay, so that concludes our brief discussion of the two-time pad. Next attack I want to mention is the fact that the one-time pad and stream ciphers in general provide no integrity at all. All they do is they try to provide confidentiality when the key is only used once. They provide no integrity at all. But even worse than that, it's actually very easy to modify ciphertexts and have known effects on the corresponding plaintexts. So let me explain what I mean by that. This property, by the way, is called malleability, and we'll see what I mean by that in just a second. So imagine we have some message M that gets encrypted. So here, it gets encrypted using a stream cipher. And the ciphertext, of course, is then going to be M XOR K. Now, an attacker intercepts the ciphertext. Well, that doesn't tell him what the plaintext is. But what he can do is now, beyond eavesdropping, he can actually become an active attacker and modify the ciphertext. So when I say modify the ciphertext, let's suppose that he XORs the ciphertext with a certain value P. Let's call this the perturbation P. Well, the resulting ciphertext then becomes M XOR K XOR P. So now let me ask you, when we decrypt the ciphertext, what is it going to decrypt to? Well, I hope everybody sees that manipulating XORs, basically the decryption becomes M XOR P. So you notice that by XORing with this pad P, the attacker was able to have a very specific effect on the resulting plaintext. Okay, so to summarize this, basically you can modify the ciphertext. These modifications are undetected, but even worse, they're undetected. They have a very specific impact on the resulting plaintext. Namely, whatever you XOR the ciphertext with is going to have that exact effect on the plaintext. So to see where this can be dangerous, let's look at a particular example. Suppose the user sends an email that starts from the words "from Bob." And the attacker basically gets to intercept the corresponding ciphertext. Well, he doesn't know what the ciphertext is, but let's just, for the sake of it, let's pretend that he actually knows that this message is actually from Bob. What he wants to do is he wants to modify the ciphertext so that the plaintext would now look like it came from somebody else. Say he wants to make it look like this message actually came from Alice. All he has is the ciphertext. Well, what he can do is he can XOR it with a certain set of 3 characters. We'll see what those 3 characters are in just a second, such that the resulting ciphertext is actually an encryption of the message from Eve. And so that now when the user decrypts that, all of a sudden he'll see, hey, this message is from Eve. It's not. He'll think this message is from Eve, not from Bob, and that might cause, the wrong thing to take place. So here, the attacker, even though he himself could not have created a ciphertext that says from Eve, by modifying an existing ciphertext, all of a sudden he was able to make the ciphertext that he could not have done without intercepting at least one ciphertext. So again, by intercepting one ciphertext, he was able to change it so now it looks like it's from Eve rather than from Bob. So just to be specific, let's look at what these 3 characters need to be. So let's look at the word Bob, and I'm going to write it in ASCII. So Bob in ASCII corresponds to 42 hex, 6F hex, and 62 hex. So little b is encoded as 62, little o is encoded as 6F. The word Eve is encoded as 45 hex, 76 hex, and 65 hex. Now when I XOR these 2 words, I'm literally going to XOR them as bit strings, so Bob XOR Eve. It's not difficult to see that what I get is the 3 characters 07, 19, and 07. So really what these 3 characters here are going to be are simply 07, 19, and 07. And by XORing these three characters at the right positions into the ciphertext, the attacker was able to change the ciphertext to look like it came from Eve rather than from Bob. So this is an example where having a predictable impact on the ciphertext can actually cause quite a bit of problems. And this is this property called malleability. And we say that the runtime pad is malleable because it's very easy to compute on ciphertexts and make prescribed changes to the corresponding plaintext. So to prevent all this, I'm going to do that actually in 2 or 3 lectures, and we're going to basically show how to add integrity to encryption mechanisms in general. But right now I want you to remember that the one-time pad by itself has no integrity and is completely insecure against attackers that actually modify the ciphertexts. In this segment I want to give a few examples of stream ciphers that are used in practice. I'm going to start with 2 old examples that actually are not supposed to be used in new systems, but nevertheless they're still fairly widely used, and so I just want to mention the names so that you're familiar with these concepts. The first stream cipher I want to talk about is called RC4, designed back in 1987. And I'm only going to give you the high-level description of it, and then we'll talk about some weaknesses of RC4 and leave it at that. So RC4 takes a variable size seed. Here I just gave as an example where it would take 128 bits as the seed size, which would then be used as the key for the stream cipher. The first thing it does is it expands the 128-bit secret key into 2048 bits, which are going to be used as the internal state for the generator. And then once it's done this expansion, it basically executes a very simple loop where every iteration of this loop outputs 1 byte of output. So essentially you can run the generator for as long as you want and generate 1 byte at a time. Now RC4 is actually, as I said, fairly popular. It's used in the HTTPS protocol quite commonly actually. These days, for example, Google uses RC4 in its HTTPS. And it's also used in WEP, as we discussed in the last segment, but of course in WEP it's used incorrectly and it's completely insecure the way it's used inside of WEP. So over the years, some weaknesses have been found in RC4, and as a result, it's recommended that new projects actually not use RC4, but rather use a more modern pseudorandom generator, as we'll discuss towards the end of the segment. So let me just mention 2 of the weaknesses. So the first one is, it's kind of bizarre basically. If you look at the second byte of the output of RC4, it turns out the second byte is slightly biased. If RC4 was completely random, the probability that the second byte happens to be equal to 0 would be exactly 1 over 256. There are 256 possible bytes. The probability that it's 0 should be 1 over 256. It so happens that for RC4, the probability is actually 2 over 256, which means that if you use the RC4 output to encrypt a message, the second byte is likely to not be encrypted at all. In other words, it'll be XORed with 0, with twice the probability that it's supposed to. So 2 over 256 instead of 1 over 256. And by the way, I should say that there's nothing special about the second byte. It turns out the first and the third bytes are also biased. And in fact, it's now recommended that if you're going to use RC4, what you should do is ignore basically the first 256 bytes of the output and just start using the output of the generator starting from byte 257. The first couple of bytes turned out to be biased, so you just ignore them. The second attack that was discovered is that in fact if you look at a very long output of RC4, it so happens that you're more likely to get the sequence 00. In other words, you're more likely to get 16 bits, 2 bytes of 00 than you should. Again, if RC4 was completely random, the probability of seeing 00 would be exactly 1 over 256 squared. It turns out RC4 is a little biased, and the bias is 1 over 256 cubed. It turns out this bias actually starts after several gigabytes of data are produced by RC4, but nevertheless this is something that can be used to predict the generator, and definitely it can be used to distinguish the output of the generator from truly random sequence. Basically, the fact that 00 appears more often than it should gives a distinguisher. And then in the last segment, we talked about related key attacks that were used to attack WEP, that basically say that if one uses keys that are closely related to one another, then it's actually possible to recover the root key. So these are the weaknesses that are known about RC4, and as a result, it's recommended that new systems actually not use RC4 and instead use a modern pseudorandom generator. Okay, the second example I want to give you is a badly broken stream cipher that's used for encrypting DVD movies. When you buy a DVD in the store, the actual movie is encrypted using a stream cipher called the Content Scrambling System, CSS. CSS turns out to be a badly broken stream cipher, and we can very easily break it, and I want to show you how the attack algorithm works. We're doing it so that you can see an example of an attack algorithm, but in fact, there are many systems out there that basically use this attack to decrypt encrypted DVDs. So the CSS stream cipher is based on something that hardware designers like. It's designed to be a hardware stream cipher that's supposed to be easy to implement in hardware, and is based on a mechanism called a linear feedback shift register. So a linear feedback shift register is basically a register that consists of cells where each cell contains 1 bit. And then basically what happens is there are these taps into certain cells, not all the cells, certain positions are called taps. And then these taps feed into an XOR, and then at every clock cycle, the shift register shifts to the left, the last bit falls off, and then the first bit becomes the result of this XOR. So you can see that this is a very simple mechanism to implement in hardware. It takes very few transistors, just a shift right. The last bit falls off, and the first bit just becomes the XOR of the previous bits. So the seed for this LFSR basically is the initial state of the LFSR, and it's the basis of a number of stream ciphers. So here are some examples. So as I said, DVD encryption uses 2 LFSRs. I'll show you how that works in just a second. GSM encryption, these are algorithms called A51 and A52. That uses 3 LFSRs. Bluetooth encryption is an algorithm called E0. These are all stream ciphers, and that uses 4 LFSRs. Turns out all of these are badly broken and actually really should not be trusted for encrypting traffic, but they're all implemented in hardware, so it's a little difficult now to change what the hardware does. But the simplest of these, CSS, actually has a cute attack on it, so let me show you how the attack works. So let's describe how CSS actually works. So the key for CSS is 5 bytes, namely 40 bits. 5 times 8 is 40 bits. The reason they had to limit themselves to only 40 bits is that DVD encryption was designed at a time where US export regulations only allowed for export of crypto algorithms where the key was only 40 bits. So the designers of CSS were already limited to very, very short keys, just 40-bit keys. So their design works as follows. Basically, CSS uses 2 LFSRs. One is a 17-bit LFSR. In other words, the register contains 17 bits. And the other one is a 25-bit LFSR. It's a little bit longer, 25-bit LFSR. And the way these LFSRs are seeded is as follows. So the key for the encryption basically looks as follows. You start off with a 1, and you concatenate to it the first 2 bytes of the key. First 2 bytes of the key. And that's the initial state of the LFSR. And then the second LFSR basically is initialized the same way. 1 concatenated the last 3 bytes of the key. 3 bytes of key, and that's loaded into the initial state of the LFSR. You can see that the first 2 bytes are 16 bits plus leading 1, that's 17 bits overall, whereas the second LFSR is 24 bits plus 1, which is 25 bits. And you notice we used all 5 bits of the key. So then these LFSRs are basically run for 8 cycles, so they generate 8 bits of output, and then they go through this adder that does basically addition modulo 256. Yeah, so this is an addition box modulo 256. There's one more technical thing that happens. In fact, what's actually also added is the carry from the previous block, but that is not so important. That's a detail that's not so relevant. Okay, so every block, you notice we're doing addition modulo 256, so we're ignoring the carry, but the carry is basically added either at 0 or 1 to the addition of the next block. Okay, and then basically this output 1 byte per round. Okay, and this byte is then of course used, it's XORed with the appropriate byte of the movie that's being encrypted. Okay, so it's a very simple stream cipher. It takes very little hardware to implement. It'll run fast even on very cheap hardware, and it will encrypt movies. So it turns out this is easy to break in time roughly 2 to the 17. In roughly 2 to the 17 time. And let me show you how. So suppose you intercept a movie. So here we have an encrypted movie that you want to decrypt. So let's say that this is all encrypted. So you have no idea what's inside of here. However, it so happens that just because DVD encryption is using MPEG files, it so happens that you know a prefix of the plaintext. Let's just say maybe this is 20 bytes. Well, we know that if you XOR these two things together, so in other words, you do the XOR here, what you'll get is the initial segment of the PRG. So you'll get the first 20 bytes of the output of CSS, the output of this PRG. Okay, so now here's what we're going to do. So we have the first 20 bytes of the output. And now we do the following. We try all 2 to the 17 possible values of the first LFSR. Okay, so 2 to the 17 possible values. So for each value, so for each of these 2 to the 17 initial values of the LFSR, we're going to run the LFSR for 20 bytes. Okay, so we'll generate 20 bytes of outputs from this first LFSR, assuming for each one of the 2 to the 17 possible settings. Now, remember, we have the full output of the CSS system. So what we can do is we can take this output that we have and subtract it from the 20 bytes that we got from the first LFSR. And if, in fact, our guess for the initial state of the first LFSR is correct, what we should get is the first 20 byte output of the second LFSR, right? Because that's, by definition, what the output of the CSS system is. Now, it turns out that looking at a 20 byte sequence, it's very easy to tell whether this 20 byte sequence came from a 25-bit LFSR or not. If it didn't, then we know that our guess for the 17-bit LFSR was incorrect. And then we move on to the next guess for the 17-bit LFSR, and the next guess, and so on and so forth, until eventually we hit the right initial state for the 17-bit LFSR, and then we'll see that the 20 bytes that we get as the candidate output for the 25-bit LFSR is in fact a possible output for a 25-bit LFSR. And then not only will we have learned the correct initial state for the 17-bit LFSR, we will have also learned the correct initial state of the 25-bit LFSR, and then we can predict the remaining output of CSS. And of course, using that, we can then decrypt the rest of the movie. We can actually recover the remaining plain text. Okay, this is things that we talked about before. So I said this a little quick, but hopefully it was clear. We are also going to be doing a homework exercise on this type of stream ciphers, and you'll kind of get the point of how these attack algorithms work. And I should mention that there are many open source systems now that actually use this method to decrypt CSS encrypted data. Okay, so now that we've seen 2 weak examples, let's move on to better examples. And in particular, the better pseudo-random generators come from what's called the eStream project. This is a project that concluded in 2008, and they qualified basically 5 different stream ciphers. But here I want to present just one. So first of all, the parameters for these stream ciphers are a little different from what we're used to. So these stream ciphers, as normal, they have a seed. But in addition, they also have what's called a nonce. And we'll see what the nonce is used for in just a minute. So they take 2 inputs, a seed and a nonce. We'll see what the nonce is used for in just a second. And then, of course, they produce a very large output. So n here is much, much, much bigger than s. Now, when I say nonce, what I mean is a value that's never going to repeat as long as the key is fixed. And I'll explain that in more detail in just a second. But for now, just think of it as a unique value that never repeats as long as the key is the same. And so, of course, once you have this PRG, you would encrypt, you get a stream cipher just as before, except now, as you see, the PRG takes as input both the key and the nonce. And the property of the nonce is that the pair k comma r, so the key comma the nonce, is never repeats. It's never used more than once. So the bottom line is that you can reuse the key because the nonce makes the pair unique, because k and r are only used once. I'll say they're unique. Okay, so this nonce is kind of a cute trick that saves us the trouble of moving to a new key every time. Okay, so the particular example from the eStream that I want to show you is called Salsa 20. It's a stream cipher that's designed for both software implementations and hardware implementations. It's kind of interesting. You realize that some stream ciphers are designed for software, like RC4. Everything it does is designed to make software implementation run fast, whereas some other stream ciphers are designed for hardware, like CSS, using an LFSR that's particularly designed to make hardware implementations very cheap. Salsa, the nice thing about that is that it's designed so that it's both easy to implement it in hardware and its software implementation is also very fast. So let me explain how Salsa works. Well, Salsa takes either 128 or 256-bit keys. I'll only explain the 128-bit version of Salsa. So this is the seed. And then it also takes a nonce, just as before, which happens to be 64 bits, and then it'll generate a large output. Now, how does it actually work? Well, the function itself is defined as follows. Basically, given the key and the nonce, it will generate a very long, a long pseudo-random sequence as long as necessary. And it'll do it by using this function that I'll denote by h. This function h takes three inputs, basically the key, the seed k, the nonce r, and then a counter that increments from step to step. So it goes from 0, 1, 2, 3, 4, as long as we need it to be. Okay, so basically by evaluating this h on this kr, but using this incrementing counter, we can get a sequence that's as long as we want. So all I have to do is describe how this function h works. And let me do that here for you. The way it works is as follows. Well, we start off by expanding the state into something quite large, which is 64 bytes long. And we do it as follows. Basically, we stick a constant at the beginning. So there's tau 0. These are 4 bytes. It's a 4-byte constant. So the spec for salsa basically gives you the value for tau 0. Then we put k in, which is 16 bytes. Then we put another constant. Again, this is 4 bytes. And as I said, the spec basically specifies what this fixed constant is. Then we put the nonce, which is 8 bytes. Then we put the index. This is the counter 0, 1, 2, 3, 4, which is another 8 bytes. Then we put another constant, tau 2, which is another 4 bytes. Then we put the key again. This is another 16 bytes. And then finally we put a third constant, tau 3, which is another 4 bytes. Okay, so as I said, if you sum these up, you see that you get 64 bytes. So basically we've expanded the key and the nonce and the counter into 64 bytes. Basically the key is repeated twice, I guess. And then what we do is we apply a function. I'll call this function little h. Okay, so we apply this function little h, and this is a function that's one-to-one, so it maps 64 bytes to 64 bytes. And it's a completely invertible function. Okay, so this function h is, as I say, it's an invertible function. So given the input, you can get the output, and given the output, you can go back to the input. And it's designed specifically so it's A, easy to implement in hardware, and B, on an x86, it's extremely easy to implement because x86 has this SSE2 instruction set, which supports all the operations you need to do for this function. It's very, very fast. As a result, also has a very fast stream cipher. And then it does this basically again and again. So it applies this function h again, it gets another 64 bytes, and so on and so forth. Basically, it does this 10 times. Okay, so the whole thing here, I'll say, repeats 10 times. So basically, apply h 10 times. And then by itself, this is actually not quite random. It's not going to look random because, like we said, h is completely invertible. So given this final output, it's very easy to just invert h and go back to the original input and then test that the input has the right structure. So you do one more thing, which is to basically XOR the input and the final output. Actually, sorry, it's not an XOR, it's actually an addition. So you do an addition word by word. So there are 64 bytes, you do a word by word addition, 4 bytes at a time, and finally you get the 64 byte output. That's it. That's the whole pseudo-random generator. So that's the whole function little h, and as I explained, this whole construction here is the function big H, and then you evaluate big H by incrementing the counter I from 0, 1, 2, 3 onwards, and that will give you a pseudo-random sequence that's as long as you need it to be. And basically there are no significant attacks on this. This has security that's very close to 2 to the 128. We'll see what that means more precisely later on, but it's a very fast stream cipher, both in hardware and in software, and as far as we can tell, seems to be unpredictable as required for a stream cipher. So I should say that the eStream project actually has 5 stream ciphers like this. I only chose Salsa because I think it's the most elegant, but I can give you some performance numbers here. So you can see these are performance numbers on a 2.2 gigahertz, x86 type machine, and you can see that RC4 actually is the slowest because essentially, well, it doesn't really take advantage of the hardware. It only does byte operations, and so there's a lot of wasted cycles that aren't being used. But the eStream candidates, both Salsa and another candidate called Sosa Manuk, I should say these are eStream finalists. These are actually stream ciphers that are approved by the eStream project, you can see that they achieve significant rates. This is 643 megabytes per second on this architecture, more than enough for a movie, and these are actually quite impressive rates. And so now you've seen examples of two old stream ciphers that shouldn't be used, including attacks on those stream ciphers. You've seen what the modern stream ciphers look like with this nonce, and you see the performance numbers for these modern stream ciphers. So if you happen to need a stream cipher, you could use one of the eStream's finalists. In particular, you could use something like Salsa. In the next three segments, we will change gears a little bit and talk about the definition of a PRG. This definition is a really good way to think of a PRG, and we will see many applications for this definition. So consider a PRG with key space k that outputs n-bit strings. Our goal is to define what does it mean for the output of the generator to be indistinguishable from random. In other words, we're going to define a distribution that basically is defined by choosing a random key in the key space. Remember that arrow with R above it means choosing uniformly from the set script k. And then we output basically the output of the generator. And what we'd like to say is that this distribution of pseudo-random strings, is indistinguishable from a truly uniform distribution. In other words, if we just choose a truly uniform string in 0, 1 to the n, and simply output this string, we'd like to say that these two distributions are indistinguishable from one another. Now, if you think about it, this sounds really surprising, because if we draw a circle here of all possible strings in 0, 1 to the n, then the uniform distribution basically can output any of these strings with equal probability. That's the definition of the uniform distribution. However, a pseudo-random distribution generated by this generator G, because the seed space is so small, the set of possible outputs is really, really small. It's tiny inside of 0, 1 to the n, and this is really all that the generator can output. And yet what we're arguing is that an adversary who looks at the output of the generator in this tiny set can't distinguish it from the output of the uniform distribution over the entire set. Okay? That's the property that we're actually shooting for. So to understand how to define this concept of indistinguishability from random, we need the concept of a statistical test. So let me define what a statistical test on 0, 1 to the n is. I'm going to define these statistical tests by the letter A. And a statistical test is basically an algorithm that takes as input an n-bit string and simply outputs 0 or 1. Now I'll tell you that 0, we're going to think of it as though the statistical test said the input you gave me is not random. And 1, we're going to think of it as saying that the input you gave me actually is random. Okay, so all the statistical test does is it basically takes the input x that was given to it, the n-bit string that was given to it, and decides whether it looks random or it doesn't look random. Let's look at a couple of examples. So the first example basically will use the fact that for a random string, the number of zeros is roughly equal to the number of ones in that string. In other words, the statistical test is going to say 1 if and only if basically the number of zeros in the given string x minus the number of ones in the given string x is these two numbers are not too far apart. In other words, the difference between the number of zeros and the number of ones, let's just say, is less than 10 times square root of n. Okay, so if the difference is less than 10 times square root of n, the statistical test will say, hey, the string x looks random. If the difference happens to be much bigger than 10 times square root of n, that starts to look suspicious, and then the statistical test will say, hey, the string you gave me does not look random. Okay, so this is our first example of a statistical test. Let's look at another similar example. We'll say here, the statistical test will say 1 if and only if, say, the number of times that we have two consecutive zeros inside of x. Well, let's think about this for a second. This basically, again, counts in this string of n bits, it counts the number of times that we see the pattern 0, 0, two consecutive zeros. Well, for a random string, we will expect to see 0, 0 with probability 1/4, and therefore in a random string, we'll expect about n over 4 0 zeros. Yeah, n over 4 blocks of 0, 0. And so what the statistical test will do is it will say, well, if the number of 0 zeros is roughly n over 4, in other words, the difference between the number and n over 4 is, say, less than 10 square root of n, then we will say that x looks random. And if the gap is much bigger than n over 4, we'll say, hey, this string doesn't really look random, and then the statistical test will output 0. Okay, so here are two examples of statistical tests that basically, for random strings, they will output 1 with very high probability. But for strings that, don't look random, for example, think of the all 0 string. For the all 0 string, neither one of these tests will output 1. And in fact, the all 0 string does not look random. Let's look at one more example of a statistical test, just to kind of show you that basically statistical tests can pretty much do whatever they want. So here's a third example. Let's say that the statistical test outputs 1 if and only if, say, the biggest block, so we'll call this the maximum run of 0 inside of the string x. This is basically the longest sequence of zeros inside of the string x. In a random string, you expect the longest sequence of zeros to be roughly of length log n. So we'll say if the longest sequence of 0 happens to be less than 10 times log n, then this test will say that x was random. But if all of a sudden we see a run of zeros that say is much bigger than 10 log n, then the statistical test will say the string is not random. Okay, so this is another crazy thing that the statistical test will do. By the way, you notice that if you give this test the all 1 string, so 1, 1, 1, 1, 1, this test will also output 1. In other words, this test will think that the all 1 string is random, even though it's not. Yeah, even though the all 1 string is not particularly random. Okay, so statistical tests don't have to get things right. They can do whatever they like. They can decide to output random or not, 0 or 1, however they like. And similarly, there are many, 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 many other statistical tests. There are literally hundreds of statistical tests that one can think of. And I can tell you that in the old days, basically the way you would define that something looks random is you would say, hey, here's a battery of statistical tests, and all of them said that the string looks random. Therefore, we say that this generator, the generator of the string, is a good generator. In other words, this definition that uses a fixed set of statistical tests is actually not a good definition for security, or more generally for crypto. But before we talk about actually defining security, the next thing we talk about is how do we evaluate whether a statistical test is good or not. So to do that, we define the concept of advantage. And so let me define the advantage. So here we have a generator that outputs n-bit strings, and we have a statistical test on n-bit strings. And we define the advantage of this generator, I'll denote it by advantage sub PRG, the advantage of the statistical test A relative to the generator G. I'll define it as follows. It's basically the difference between two quantities. The first quantity is basically we ask how likely is the statistical test to output 1 when we give it a pseudorandom string. Okay, so here k is chosen uniformly from the seed space. And we ask how likely is the statistical test to output 1 when we give it a pseudorandom output generated by the generator. Versus now we ask how likely is the statistical test to output 1 when we give it a truly random string. So here R is truly random in 0, 1 to the n. Okay? And yeah, we look at the difference between these two quantities. Now you realize because these are differences of probabilities, this advantage is always going to lie in the interval 0, 1. So let's think a little bit about what this advantage actually means. So first of all, if the advantage happens to be close to 1, well, what does that mean? That means that somehow the statistical test A behaved differently when we gave it pseudo-random inputs, when we gave it the output of the generator, from when we gave it truly random inputs, right? It somehow behaved differently. In one case, it output 1 with a certain probability, and in the other case, it output 1 with a very different probability. Okay, so somehow it was able to behave differently, and what that really means is that the statistical test can basically distinguish the output of the generator from random. Okay, so in some sense we'll say that the statistical test broke the generator G because it was able to distinguish the output from random. However, if the advantage is close to 0, well, what does that mean? That means that basically the statistical test behaves pretty much the same on pseudo-random inputs as it does on truly random inputs. And basically there we would say that A could not distinguish the generator from random. Okay, so this gives you a little bit of intuition about why this concept of advantage is important. It basically tells us whether A was able to break the generator, namely distinguish it from random, or not able to break it. So let's look first of all at a very silly example. Suppose we have a statistical test A that simply ignores its inputs and always outputs 0. Okay, it always outputs 0. What do you think is the advantage of the statistical test relative to a generator G? So I hope everybody said the advantage is 0. Let me just explain why that's the case. Well, if the statistical test always outputs 0, that means that when we give a pseudo-random input, it will never output 1. So the probability that it outputs 1 is 0. Similarly, when we give a truly random input, it still will never output 1. And so the probability that it outputs 1 is 0. And so 0 minus 0 is 0. So its advantage is 0. So basically, a statistical test that ignores its input is not able to distinguish truly random input from a pseudo-random input, obviously. Okay, so now let's look at a more interesting example. So suppose we have a generator G that satisfies a funny property. It so happens that for 2/3 of the keys, the first bit of the output of the generator happens to be 1. Okay, so if I choose a random key with probability 2/3, the generator will output 1 as its first bit. Okay, so that's the property of the generator that we're looking at. Now let's look at the following statistical test. The statistical test basically says, if the most significant bit of the string you gave me is 1, I'm going to say 1, meaning I think it's random. If the most significant bit of the string you gave me is not 1, well, namely 0, I'm going to say 0. Okay, so now my question to you is, what is the advantage of this statistical test on the generator G? Okay, so remember I just wrote down the definition here again, and I'll let you think about this for a second. So let me explain. Suppose we give the statistical test pseudo-random input. By definition of G, we know that with probability 2/3, the first bit in the input will start with the bit 1. But if it starts with the bit 1, then the statistical test will output 1. In other words, the probability that the statistical test outputs 1 is exactly 2/3. Now let's look at the case of a random string. If I give you a random string, how likely is it that the most significant bit of the random string is 1? Well, for a random string, that happens exactly half the time. And so in this case, the statistical test will output 1 with probability 1/2. And so the overall advantage is 1/6, and 1/6 is actually a non-negligible number. That's actually a fairly large number, which basically means that this A was able to distinguish the output. We'll say that A breaks the generator G with advantage 1/6. Okay, which basically means that this generator is no good, is broken. Okay, so now that we understand what statistical tests are, we can go ahead and define what is a secure pseudo-random generator. So basically we say that a generator G is secure if essentially no efficient statistical test can distinguish its output from random. More precisely, what we'll say is that basically for all efficient statistical tests A, it so happens that if I look at the advantage of the statistical test A relative to G, this advantage basically is negligible. Okay, so in other words, it's very close to 0, and as a result, this statistical test was not able to distinguish the output from random, and that has to be true for all statistical tests. So this is a very, very pretty and elegant definition that says that a generator is secure not only if a particular battery of statistical tests says that the output looks random, but in fact all efficient statistical tests will say the output looks random. Okay? One thing I'd like to point out is that the restriction to efficient statistical tests is actually necessary. If we ask that all statistical tests, regardless of whether they're efficient or not be able to distinguish the output from random, then in fact that cannot be satisfied. So in other words, if we took out the requirements that the test be efficient, then this definition would be unsatisfiable, and I'll leave this as a simple puzzle for you to think about. But basically the fact is that restricting this definition to only efficient statistical tests is actually necessary for this to be satisfiable. Now that we have a definition, the next question is, can we actually construct a generator and then prove that in fact it is a secure PRG? In other words, prove that no efficient statistical test can distinguish its output from random. And it turns out that the answer is we actually can't. In fact, it's not known if there are any provably secure PRGs. And I'll just say very briefly, the reason is that if you could prove that a particular generator is secure, that would actually imply that P is not equal to NP. And I don't want to dwell on this because I don't want to assume you guys know what P and NP are. But I'll just tell you as a simple fact that in fact if P is equal to NP, then it's very easy to show that there are no secure PRGs. And so if you could prove to me that a particular PRG is secure, that would imply that P is not equal to NP. Again, I will leave this to you as a simple puzzle to think about. But even though we can't actually rigorously prove that a particular PRG is secure, we still have lots and lots and lots of heuristic candidates, and we even saw some of those in the previous segment. Okay, now that we understand what is a secure PRG, I want to talk a little bit about some applications and implications of this definition. And so the first thing I want to show you is that in fact a secure PRG is necessarily unpredictable. In a previous segment, we talked about what it means for a generator to be unpredictable, and we said that basically what that means is that given a prefix of the output of the generator, it's impossible to predict the next bit of the output. Okay, so we'd like to show that if a generator is secure, then necessarily it means it's unpredictable. And so the way we're going to do that is using the contrapositive. That is, we're going to say that if you give me a generator that is predictable, then necessarily it's insecure. In other words, necessarily I can distinguish it from random. And so let's see, this is actually a very simple fact, and so let's see how we would do that. So suppose you give me a predictor. In other words, suppose you give me an efficient algorithm such that, in fact, if I give this algorithm the output of the generator, but I give it only the first I bits of the output, it's able to predict the next bit of the output. In other words, given the first I bits, it's able to predict the I plus first bit, and it does that with a certain probability. So let's say if we choose a random k from the key space, then clearly a dumb predictor would be able to predict the next bit with probability 1/2, simply just guess a bit. You'll be right with probability 1/2. However, this algorithm A is able to predict the next bit with probability 1/2 plus epsilon. So it's bounded away from 1/2, and in fact we require that this be true for some non-negligible epsilon. So for example, epsilon equals 1/1000 would already be a dangerous predictor because it can predict the next bit given a prefix with non-negligible advantage. Okay, so suppose we have such an algorithm. Let's see that we can use this algorithm to break our generator. In other words, to show that the generator is distinguishable from random and therefore is insecure. So what we'll do is we'll define a statistical test. So let's define a statistical test B as follows. Basically, B given a string x, what it will do is it will simply run algorithm A on the first I bits of the string x that it was given, and statistical test B is simply going to ask, was A successful in predicting the I plus first bit of the string? If it was successful, then it's going to output 1, and if it wasn't successful, then it's going to output 0. Okay, this is our statistical test. Let's put it in a box so we can take it wherever we like, and we can run the statistical test on any n-bit string that's given to us as input. So now let's look at what happens. Suppose we give the statistical test a truly random string, so a truly random string R, and we ask what is the probability that this statistical test outputs 1? Well, for a truly random string, the I plus first bit is totally independent of the first I bits. So whatever this algorithm A is going to output is completely independent of what the I plus first bit of the string R is. And so whatever A outputs, the probability that it's going to be equal to some random bit xi plus 1, random independent bit xi plus 1, that probability is exactly 1/2. In other words, algorithm A simply has no information about what the bit xi plus 1 is, and so necessarily the probability that it's able to predict xi plus 1 is exactly 1/2. On the other hand, let's look at what happens when we give our statistical test a pseudo-random sequence. Okay, so now we're going to run the statistical test on the output of the generator, and we ask how likely is it to output 1? Well, by definition of A, we know that when we give it the first I bits of the output of the generator, it's able to predict the next bit with probability 1/2 plus epsilon. So in this case, our statistical test B will output 1 with probability greater than 1/2 plus epsilon. And basically what this means is if we look at the advantage of our statistical tests over the generator G, it's basically the difference between this quantity and that quantity. And the difference between the two, you can see, is clearly greater than an epsilon. So what this means is that if algorithm A is able to predict the next bit with advantage epsilon, then algorithm B is able to distinguish the output of the generator with advantage epsilon. Okay, so if A is a good predictor, B is a good statistical test that breaks the generator. And as we said, the contrapositive of that is that if G is a secure generator, then there are no good statistical tests, and as a result, there are no predictors. Okay, and which means that the generator is, as we said, unpredictable. Okay, so far what we've seen is that if the generator is secure, necessarily it's impossible to predict the I plus first bit given the first I bits. Now, there's a very elegant and remarkable theorem due to Yao back in 1982 that shows that in fact the converse is also true. In other words, if I give you a generator that's unpredictable, so you cannot predict the I plus first bit from the first I bits, and that's true for all I, that generator in fact is secure. Okay, so let me state the theorem a little bit more precisely. So here we have our generator that outputs n-bit outputs. The theorem says the following: basically for all bit positions, it's impossible to predict I plus first bit of the output given the first I bits, and that's true for all I. In other words, again, the generator is unpredictable for all bit positions. Then that in fact implies that the generator is a secure PRG. I want to paraphrase this in English, and so the way to kind of interpret this result is to say that if basically these next bit predictors, these predictors that try to predict the I plus first bit given the first I bits, if they're not able to distinguish G from random, then in fact no statistical test can distinguish G from random. So kind of next bit predictors are in some sense universal predictors when it comes to distinguishing things from random. This theorem, by the way, it's not too difficult to prove, but there's a very elegant idea behind its proof. I'm not going to do the proof here, but I encourage you to think about this as a puzzle and try to kind of prove this theorem yourself. Let me show you kind of one cute implication of this theorem. So let me ask you the following question. Suppose I give you a generator, and I tell you that given the last bit of the output, it's easy to predict the first bit of the outputs. Okay, so given the last n bits, you can compute the first n bits. That's kind of the opposite of predictability, right? Predictability meant given the first bits, you can produce the next bits. Here, given the last bits, you can produce the first ones. And my question to you, does that mean that the generator is predictable? Can you somehow, from this fact, still build a predictor for this generator? So this is kind of a simple application of Yao's theorem, and let me explain to you. The answer is actually yes. Let me explain why. How do we build this generator? Well, actually, we're not going to build it. I'm just going to show you that the generator exists. Well, because the last n over 2 bits imply the first n over 2 bits, that necessarily means that the generator, here, let me write it this way, that necessarily means that G is not secure. Because just as we did before, it's very easy to build a statistical test that will distinguish the output of G from uniform. So G is not secure. But if G is not secure, by Yao's theorem, that means that G is predictable. So in other words, there exists some I for which, given the first I bits of the output, you can build the I plus first bit of the output. Okay? And so even though I can't quite point to you to a predictor, we know that a predictor must exist. So that's one cute, simple application of Yao's theorem. Now, before we end this segment, I want to kind of generalize a little bit what we did and introduce a little bit of important notation that's going to be useful actually throughout. So we're going to generalize the concept of indistinguishability from uniform to indistinguishability of two general distributions. So suppose I give you P1 and P2, and we ask, can these two distributions be distinguished? And so we'll say that the distributions are computationally indistinguishable, and we'll denote this by P1 is squiggly P, P2. This means that in polynomial time, P1 cannot be distinguished from P2, and we'll say that they're indistinguishable basically just as before, if basically for all efficient statistical tests A, it so happens that if I sample from the distribution P1 and I give the output to A, versus if I sample from the distribution P2 and I give the sample to A, then basically A behaves the same in both cases. In other words, the difference between these two probabilities is negligible. And this has to be true for all statistical tests, for all efficient statistical tests. Okay, so if this is the case, then we say that, well, A couldn't distinguish, its advantage in distinguishing two distributions is negligible, and if that's true for all efficient statistical tests, then we say that the two distributions are basically computationally indistinguishable because an efficient algorithm cannot distinguish them. And just to show you how useful this notation is, basically using this notation, the definition of security for a PRG just says that if I give you a pseudo-random distribution, in other words, I choose k at random and then output g of k, that distribution is computationally indistinguishable from the uniform distribution. So you can see this very simple notation captures the whole definition of pseudorandom generators. Okay, so we're going to make use of this notation in the next segment when we define what does it mean for a cipher to be secure. My goal for the next two segments is to show you that if we use a secure PRG, we get a secure stream cipher. The first thing we have to do is define what does it mean for a stream cipher to be secure. So whenever we define security, we always define it in terms of what can the attacker do and what is the attacker trying to do. In the context of stream ciphers, remember these are only used with a one-time key, and as a result, the most the attacker is ever going to see is just one ciphertext encrypted using the key that we're using. And so we're going to limit the attacker's abilities to basically obtain just one ciphertext. And in fact, later on, we're going to allow the attacker to do much, much, much more. But for now, we're just going to give him one ciphertext. And we want to define what does it mean for the cipher to be secure. So the first definition that comes to mind is basically to say, well, maybe we want to require that the attacker can't actually recover the secret key. Okay, so given the ciphertext, he shouldn't be able to recover the secret key. But that's a terrible definition because think about the following brilliant cipher. So here, but the way we encrypt a message using a key k is basically we just output the message. Okay, this is a brilliant cipher. Yeah, of course, it doesn't do anything. Given a message, it just outputs the message as the ciphertext. So this is not a particularly good encryption scheme. However, given the ciphertext, namely the message, the poor attacker cannot recover the key because he doesn't know what the key is. And so as a result, this cipher, which clearly is insecure, would be considered secure under this requirement for security. So this definition will be no good. Okay, just recovering the secret key is the wrong way to define security. So the next thing we can try and attempt is basically to say, well, maybe the attacker doesn't care about the secret key. What he really cares about is the plaintext. So maybe it should be hard for the attacker to recover the entire plaintext. But even that doesn't work because let's think about the following encryption scheme. So suppose what this encryption scheme does is it takes two messages. So I'm going to use two lines to denote the concatenation of two messages. M0 line M1 means concatenate M0 and M1. And imagine what the scheme does is really it outputs M0 in the clear and concatenates to that the encryption of M1, perhaps even using the one-time pad. Okay? And so here the attacker is going to be given one ciphertext, and his goal would be to recover the entire plaintext. But the poor attacker can't do that because here maybe we encrypted M1 using the one-time pad, so the attacker can't actually recover M1 because we know the one-time pad is secure given just one ciphertext. So this construction would satisfy the definition, but unfortunately, clearly this is not a secure encryption scheme because we just leaked half of the plaintext. M0 is completely available to the attacker. So even though he can't recover all of the plaintext, he might be able to recover most of the plaintext, and that's clearly insecure. So of course we already know the solution to this, and we talked about Shannon's definition of security, perfect secrecy, where Shannon's idea was that in fact when the attacker intercepts a ciphertext, he should learn absolutely no information about the plaintext. He shouldn't even learn one bit about the plaintext, or even he shouldn't even be able to predict a little bit about a bit of the plaintext. Absolutely no information about the plaintext. So let's recall very briefly Shannon's concept of perfect secrecy. Basically we said that, given a cipher, we said the cipher has perfect secrecy if given two messages of the same length. It so happens that the distribution of ciphertexts, if we pick a random key and we look at the distribution of ciphertext, we encrypt M0, we get exactly the same distribution as when we encrypt M1. The intuition here was that if the adversary observes the ciphertext, then he doesn't know whether it came from the distribution, the result of encrypting M0, or it came from the distribution as the result of encrypting M1. And as a result, he can't tell whether we encrypted M0 or M1. And that's true for all messages of the same length. And as a result, the poor attacker doesn't really know what message was encrypted. Of course, we already said that this definition is too strong in the sense that it requires really long keys. If a cipher that has short keys can't possibly satisfy this definition, and in particular stream ciphers can't satisfy this definition. Okay, so let's try to weaken the definition a little bit, and let's think to the previous segment, and we can say that instead of requiring that the two distributions be absolutely identical, what we can require is that the two distributions just be computationally indistinguishable. In other words, a poor, efficient attacker cannot distinguish the two distributions, even though the distributions might be very, very, very different. But just given a sample for one distribution and a sample from another distribution, the attacker can't tell which distribution he was given a sample from. It turns out this definition is actually almost right, but it's still a little too strong. This still cannot be satisfied. So we have to add one more constraint, and that is that instead of saying that this definition should hold for all M0, M1, it needs to hold for only pairs M0, M1 that the attacker can actually exhibit. Okay, so this actually leads us to the definition of semantic security. And so, again, this is semantic security for a one-time key. In other words, when the attacker is only given one ciphertext. And so the way we define semantic security is by defining two experiments. Okay, we'll define experiment 0 and experiment 1. And more generally, we'll think of these as experiment parenthesis B, where B can be 0 or 1. Okay, so the way the experiment is defined is as follows. We have an adversary that's trying to break the system, an adversary A. That's kind of the analog of a statistical test in the world of pseudo-random generators. And then the challenger does the following. So really we have two challengers, but the challengers are so similar that we can just describe them as a single challenger that in one case takes as input the bit set to 0, and the other case takes as input the bit set to 1. And let me show you what these challengers do. The first thing the challenger is going to do is it's going to pick a random key, and then the adversary basically is going to output two messages M0 and M1. Okay, so this is an explicit pair of messages that the attacker wants to be challenged on. And as usual, we're not trying to hide the length of the messages. We require that the messages be equal length. And then the challenger basically will output either the encryption of M0 or the encryption of M1. Okay, so in experiment 0, the challenger will output the encryption of M0. In experiment 1, the challenger will output the encryption of M1. Okay, so that's the difference between the two experiments. And then the adversary is trying to guess, basically, whether he was given the encryption of M0 or given the encryption of M1. Okay, so here's a little bit of notation. Let's define the event WB to be the event that in experiment B, the adversary output 1. Okay, so that's just an event. That basically in experiment 0, W0 means that the adversary output 1. In experiment 1, W1 means the adversary output 1. And now we can define the advantage of this adversary, basically to say what this is called the semantic security advantage of the adversary A against the scheme E, to be the difference of the probability of these two events. In other words, we're looking at whether the adversary behaves differently when he was given the encryption of M0 from when he was given the encryption of M1. And I want to make sure this is clear, so I'm going to say it one more time. So in experiment 0, he was given the encryption of M0. In experiment 1, he was given the encryption of M1. Now, we're just interested in whether the adversary output 1 or not in these experiments. If in both experiments the adversary output 1 with the same probability, that means that the adversary wasn't able to distinguish the two experiments. Experiment 0 basically looks to the adversary the same as experiment 1, because in both cases it output 1 with the same probability. However, if the adversary is able to output 1 in one experiment with significantly different probability than in the other experiment, then the adversary was actually able to distinguish the two experiments. Okay? So, to say this more formally, essentially the advantage, again, because it's a difference of two probabilities, the advantage is a number between 0 and 1. If the advantage is close to 0, that means that the adversary was not able to distinguish experiment 0 from experiment 1. However, if the advantage is close to 1, that means the adversary was very well able to distinguish experiment 0 from experiment 1, and that really means that he was able to distinguish an encryption of M0 from an encryption of M1. Okay, so that's our definition. Actually, that's just the definition of the advantage, and then the definition is just what you would expect. Basically, we'll say that a symmetric encryption scheme is semantically secure if for all efficient adversaries, here I'll put this in quotes again, for all efficient adversaries, the advantage is negligible. In other words, no efficient adversary can distinguish the encryption of M0 from the encryption of M1. And basically this is what it says repeatedly, that for these two messages that the adversary was able to exhibit, he wasn't able to distinguish these two distributions. Now, I want to show you, this is actually a very elegant definition. It might not seem so right away, but I want to show you some implications of this definition, and you'll see exactly why the definition is the way it is. Okay, so let's look at some examples. So the first example is, suppose we have a broken encryption scheme. In other words, suppose we have an adversary A that somehow, given the ciphertext, he's always able to deduce the least significant bit of the plaintext. Okay, so given the encryption of M0, this adversary is able to deduce the least significant bit of M0. So that's a terrible encryption scheme because it basically leaks the least significant bit of the plaintext just given the ciphertext. So I want to show you that the scheme is therefore not semantically secure. So that kind of shows that if a system is semantically secure, then there is no attacker of this type. Okay, so let's see, why is the system not semantically secure? Well, so what we're going to do is we're going to basically use our adversary, who's able to learn the least significant bits. We're going to use him to break semantic security. So we're going to use him to distinguish experiment 0 from experiment 1. Okay, so here's what we're going to do. We're algorithm B. We're going to build algorithm B. And this algorithm B is going to use algorithm A in its belly. Okay, so the first thing that's going to happen is, of course, the challenger is going to choose a random key. The first thing that's going to happen is we need to output two messages. The messages that we're going to output basically are going to have different least significant bits. So one message is going to end with 0, and one message is going to end with 1. Now, what is the challenger going to do? The challenger is going to give us the encryption of either M0 or M1, depending on whether we're in experiment 0 or in experiment 1. And then we just forward this ciphertext to the adversary. Okay, to adversary A. Now, what's the property of adversary A? Given the ciphertext, adversary A can tell us what the least significant bits of the plaintext is. In other words, the adversary is going to output the least significant bit of M0 or M1. But lo and behold, that's